Good. So, a new voice, a new topic, which is, I guess, good if you have such a full workshop. Copulas and dependence. Who of you has so far not heard about the notion of copulas? Nobody? That's good. Or probably I should have done it the other way around. Good, then we can go to the next topic.
You would not be willing to give a definition of a copula if singled out of the audience. Everyone would be willing to.
Okay. Then you can probably also tell me why copulas are interesting. Well, the first point is, of course, Paul also mentioned this in his introduction yesterday morning. If I had asked the same question 20 years ago, I would have had to raise my hands, of course. And maybe 15 years ago, most of you would have risen their hands, but it is a concept that has become very popular in financial mathematics, insurance mathematics, and risk management. And there are a number of reasons for that, and we hope to sort of convince you that they can be useful in certain contexts. Copulas are, well, so far what we have done is what you would do in standard probabilistic modeling. We have a high-dimensional random vector, or maybe low-dimensional one, and we've looked at its multivariate distribution all together. And if you look at a multivariate distribution, you basically have two things. You have marginal distributions, distributions for each component, and you have the joint distribution, and somehow, of course, something like dependence. How do the different components move together? Is it quite likely that one risk will be large relative to its median, say, whenever another risk is large or not? That is dependence. And copulas are mathematical objects that help us to understand dependence. That is one reason for looking at them, for discussing them. They will also help us discover certain pitfalls when we think about measures of dependence. When I ask you, you have to measure dependence, what should we do? You would tell me probably something like, if you're not completely spoiled by this type of courses here, you would say, well, I compute correlations or something. And which is very often also the right thing to do. And so, but using copulas as a tool, as a pedagogical or as an analytical tool, we can understand a little bit when standard correlation is a good measure of dependence, when it is not, what the weaknesses are, and so on. So that's the one bit, the pedagogical bit, if you want. Copulas, there's another reason why copulas have become quite popular in the financial world, and that is model building. And it happens in finance and insurance relatively frequently that you are in a situation where you know quite a lot about the marginal distributions, but relatively little about the joint distribution. And you want to build a model, say for simulation purposes, economic scenario analysis, that respects this marginal information you have. To give you an example, a slightly stylized, 15 or 20 years ago, when I was still a young postdoc in Zurich, together with Alex, under Paul's guidance, we had a look at the risk management, risk-adjusted capital system of Swiss Re. Is there anybody from Swiss Re? Oh. And so it was very interesting because we should look at it from a methodological point of view. I guess some of the questions we asked were complete nonsense, but occasionally we also stumbled upon something. And one of the problems they had is they really wanted to compute the profit and loss distribution for the whole company, say over the time horizon of 1 year. And they had underwriting losses and actuaries and all of that, and they had developed a certain model, and they had the investment people who had developed a certain model which was more or less a version of risk metrics. And these models were standing there, two completely different computer systems. Of course, the investment guys thought that the actuaries are stupid, and the actuaries thought that the investment guys are gamblers. They didn't want to talk to each other. And still, somehow they wanted to aggregate these risks, and it was clear that they couldn't simply assume independence. And so somehow a mathematical tool was needed where you take these two distributions and merge them together to a joint distribution in a way that is mathematically consistent and that respects these given marginal distribution information. Another, it's a little bit stylized, of course. Another example is, say you want to do something like pricing an option on a basket of stocks, say a call option on the sum of two, or say for simplicity on the sum of two stocks. And both stocks are fairly liquid, and so you want to do this in line with the market. In line with the market means that the model you're using should respect, of course, the current price of the underlying, that is clear, but it should also be in line with the prices of options on each of these single stocks. And if these are liquid stocks, there's also a fairly liquid option market, and those of you who have had some finance know that essentially when you have options on a single stock, you can infer the marginal distribution of the stock at the maturity date of the option from the option prices. While to do that, you will need them for all strikes K and R, but if you have, say, 10 different strikes, you can at least approximate this distribution pretty well. So you might say, well, more or less we know what this distribution is, but to price an option on the sum, you need the joint distribution, and there you know much less. There are no options out there on the sum, or very little. And so one way of approaching this problem could be to use sort of, again, these copulas and glue together the given margins to a joint distribution that gives you, that respects these margins, and then you can compute use risk-neutral prices to compute your option prices from that. The last example, those of you, I don't know how many, are there who've really followed a couple of courses in financial math. The last example also points a little bit to limits of copula theory, because if you really wanted to do option pricing, then you would also have to think about hedging. And when you think about hedging, you need not only the distribution at the terminal date, you need an assumption about the dynamics of the stock prices. So some model of the ST is something dW plus something dt or something like that. And then you can compute hedging strategies, and you would have to generate the, say, distribution at the end from assumptions about infinitesimal correlations and volatilities, or maybe daily correlations and volatilities, things like that. If you want to do this type of dynamic modeling, then copulas are less useful, that's less natural. Then you should think about stochastic processes, but even there you can use them. But if you're in a typical risk management situation where you really say in a credit portfolio, in a loan portfolio or something, when you really have the situation that you're standing here at time 0 and here is t equals 1, and you're interested in your profit and loss distribution here, and you don't really care what happens between here and here because you cannot do anything about it anyhow. In a loan portfolio, you more or less have your portfolio fixed, and it's hard to manage. In reinsurance, maybe you're bound to your contracts anyhow. Maybe some of them were not such a good idea, but you cannot do anything about it. When you have such a static situation and you need to glue together marginal distributions, then copulas are maybe the right tool. And this reason that you very often have a lot of marginal information and relatively little joint information is, at least to me, Paul can maybe contradict me, the main reason why copulas have become so popular in the finance and insurance and risk management world. Good. After this grand introduction, we should define what a copula is, and the definition, to those of you who have not heard about it, is always a little bit disappointing. A copula is simply a distribution function with uniform margins. So the simplest situation, let's maybe go one down. There is sort of the picture I need. Uniform margins, it means that if we take d equals 2, so 2 dimensions, that's enough for our purposes here. Then, there's the point, okay, that's empty. That's good. So it's a distribution function on the unit square. And for instance, this black dot here would be C of A1, A2. This is the area of this rectangle, and so on. And whenever we compute marginal distributions, for instance, such the the probability of such a rectangle here, we should get A1 because we have uniform margins. And that's the definition. If you really want to look at the function C and check if it's a copula or not, then you have to check if it fulfills the following three properties. It should be 0 if at least one of the j's use is 0. You should have the standard uniform margins. And the last property, the property of being d-increasing, essentially means that the probability of any rectangle A1, B1 up to AD, BD, where A is always smaller than B, should be positive. Now, this one in particular looks ugly, and the nice thing about it is that you can forget about it immediately, because all copulas we're going to get, whenever we have something, it's very rarely that you write down a C and then you want to see if this is a copula or not. Typically, you have some probabilistic construction, and that's why you already know that this is a distribution function. You have to check that you have your uniform margins. The other question you might ask is why on E is, okay, uniform margins, why on Earth uniform margins, why not something else? And
just one comment. You define a distribution function on RD, whereas here you define copula on
it means that the support is 0, 1. Of course, you can extend it to RD in the obvious way. But support of, it's a distribution function on RD whose support is the d-dimensional unit cube. Good. And so the question remains, of course, why should such a simple object be able to do these tasks of creating models and helping us to understand dependence? The answer to that is a very famous theorem known as class theorem, and I'll come to that in a minute. But before, we need a few tools from probability 101, which I quickly need to recall, namely the probability and the quantile transform. These are very useful transformations, in particular for simulation and for understanding copulas. Probability transform, if you take a random variable whose distribution function f is continuous, so that the random variable has no point mass anywhere, then you do the probability transform, that is, you consider f of x. And then you know that f of x is uniformly distributed. So you can do this with a normal or a log normal or a gamma or an exponential or whatever distribution. As long as it has no point mass, as long as the distribution function is continuous, f of x is uniformly distributed. The idea of the proof is given here. So the probability that f of x is smaller or equal to u is the probability that so let's apply f to the minus 1 on both sides, which is strictly increasing as f is continuous. F of minus 1 of f of x is smaller than f of minus 1 of u. That's the probability that x is smaller than f of minus 1 of u. That's f of minus 1 of u, and that's u. And if you want to be pedantic, you can check that all of these f concatenated with f to the minus 1 stuff and so on still works when f is not strictly increasing. Of course, it does not work when f is not continuous, because then the range of f does not contain all of 0, 1. As an extreme case, take a degenerate distribution of a point mass. The distribution function is, say, point mass at 0. Distribution function is 0 to the left of 0, then jumps to 1. And this random variable, you can transform it as you want. The transform will take only one value and cannot be uniformly distributed. You would have to introduce additional randomness if you wanted to transform that to a uniform. But we don't need this now. Good. Sort of the brother or sister is the quantile transformation. If you have a uniform random variable, and if f is an arbitrary distribution function, continuous or not, then the random variable x equal to f to the minus 1 of u has distribution f. And that's, of course, very useful for simulating if you're able to compute, to generate uniform random numbers, and if you can compute the quantile transformation of your target distribution, if necessary numerically, you can simulate from that. And that's, of course, one of the reasons why all random number generators, or many random number generators, give you uniform random numbers. Good. And armed with these tools, we can now understand Scarcity Theorem, which is the most important stuff in here. There's two parts. The first part, if we have an arbitrary distribution function with margins f1 up to fd, then we can write it in a very special way. Then we can find a copula C such that the joint distribution function can be written as C applied to the marginal distribution functions. The C is uniquely defined. Okay, that's a little bit complicated. So the first thing, if the Fi's are continuous, then the C is uniquely defined. Otherwise, it's only completely defined on the range of these Fj's. If a distribution function is continuous, then its range is all of 0, 1, and the copula is uniquely defined everywhere. And copulas for discrete distributions, well, I find them a mess. There are a few colleagues who enjoy studying them, but, well, there are also people who do triathlon, so. Johanna's not here. Okay, good. And the copula can be written in the following way. It's the joint distribution function applied to the quantile functions of the marginals. Conversely, that's the first part. Conversely, if you are given any copula and univariate distribution functions, then you will be able, then this here really, this guy here, really is a distribution function. Let's put it less sophisticated. Then we know how to construct a model such that the random vector has a marginal distribution f1 up to fd, and copula C, that is the distribution, is of this form. Good. Now, we're doing not an academic lecture, we're doing an applied lecture. So normally, proofs should go to the appendix, which nobody reads. This is an exception, and the reason is that the proof is really a constructive one in the sense that it tells you where the copula comes from, how to, for the first statement, and for the second one, how to construct the desired model. So if you want to do this on your computer, and we'll do this after coffee, probably, you need to know this proof because it tells you exactly what you have to do. The existence part, we do it only for continuous f. If you want to have the full story, read the book. Good. So we have our random vector x, which has distribution function f. And then we apply the probability transform component-wise. So we take the first component, transform it with its marginal distribution, the second, transform it with the second marginal distribution, and so on. Because all these f's are continuous, we may apply this result on the probability transform, and we know that this uj, which is f j of xj, where is it? Uj, if we want to do that, I need to go a little bit back. Uj is fj of xj, that this is uniformly distributed. Okay. Now I take this random vector u, which consists of u1 up to ud, and it has a distribution function. And that distribution function has uniform margins, because u's have uniform margins. And so this distribution function is a copula by definition. A copula is a distribution function with uniform margins. And this is exactly the C in this representation according to class theorem. And to see that this is exactly true, we do the following arguments. The fj's are increasing on the range of x we can write f of x as the probability that xj is smaller or equal to capital Xj is smaller or equal to small xj for all j. That's the definition of the joint distribution function. You recognize a notation convention. Boldface are always vectors and non-boldface are numbers. Here this is really important. We may write the xj as f to the minus 1 of uj, where these uj's are just these uniform vectors we constructed here. So we get that this is the same as the probability that uj is smaller than fj for all j. And because the uj have distribution function c, this is c of f1 up to fd. So c is a copula and satisfies this relation here, the first one from Scarcity Theorem. So once again in words, what do we have to do to get the copula? The copula is just the distribution function of the random vector if we transform each of its components to uniform using the probability transformation. At least in the case where all these f's are continuous. Otherwise, you have to do triathlon. And if you want to have the C, say, analytically, now I've characterized it, I would sort of know it. I can also do that simply by applying, I know that by using this rule here. I'm taking my rule f of x1 up to xt is equal to c of f1 of x1 fd of xt. This sort of works for any x1 up to xt, and I apply it to points of the form xi is equal to fi to the minus 1 of ui. And if I do that, I know that f of f to the minus 1 of ui is equal to xi, and I get that c of f to the f, let's read this maybe from here, f of f to the minus 1 of u1 up to fd to the minus 1 of ud is, that's the c of f1 of f minus 1 of u1, fd of fd to the minus 1 of ud, and that's c of u1 ud. Now if we look at that, what we see is the following. The copula here is equal to this expression. This expression contains f, and it contains the quantile functions of all the marginals. Now, the marginals are determined from the multivariate distribution, and so are then the quantile functions. So this object here is determined once you know f, so the c is unique. That's the first part, the part that tells us how to decompose a multivariate distribution into margins and copulas. The second one is the model construction part, or if you want, the simulation part. Imagine now we have done a model, we've chosen that, okay, we know, taking my Swiss Re example, our underwriting losses are t-distributed with 4 degrees of freedom and certain parameters, our investment losses, whatever our underwriting losses, are log gamma distributed because Paul told us this morning that this is such a nice distribution. We also know the parameters there, and God told us that the joint distribution has a Gauss copula with whatever that is, with correlation parameter 0.4. That is our C. I will tell you about the Gauss copula later on. And now we want to simulate realizations of jointly underwriting and investment losses. How to do that? That's the second part. We want to simulate. Good. So the first thing is we need to generate a random vector u that follows the distribution function c. How to do that depends on the chosen copula. We'll see how to do this for the Gauss copula in a few minutes. And then what you do is very simple. You take each of these components and you apply the quantile transformation of your target distribution to it. So in my example, the first is the investment, the second one is the underwriting, say. So you would apply the quantile transformation corresponding to this T4 distribution to the first component, the quantile function of the log gamma distribution to the second, and then you would get the desired realization from your multivariate distribution function. To see that this is true, follow these lines here. The probability that x is smaller than x constructed in that way, is by definition probability that fj to the minus 1 of uj is smaller than xj. That's a probability that uj is smaller than fj of xj, and because you have distribution function c, that c of f1 up to f of x1 up to fd of xd. So to get, for the model construction part, you have to first sort of generate a realization of the copula and then apply the quantile transformation. The language, a copula model for a random vector means that the distribution function f can be written in this way, or we also say that x has copula c if f of x can be written in that way. Of course, this terminology makes most sense whenever x has continuous margins, because then this copula is unique. The next invariance principle, well, at first it sounds quite innocuous, but in fact it's a nice result. I told you in my introduction that copulas are objects that should measure dependence. And so dependence means a tendency of things are dependent if they go in the same direction, sort of positively dependent. Two risks are negatively dependent if one is large and then the other one is most of the time sort of small. That's the intuition. Now, if you think about it, this intuition, well, that's the intuition of dependence. And if this is the intuition of dependence, a measure of dependence should give you the same answer if you apply a whenever you apply a strictly increasing transformation to each of the components, because then after a strictly increasing transformation, risks still move in the same direction or still move in the opposite direction. That is not changed. And that means that a mathematical object that measures or models dependence should be invariant under strictly increasing transformations of the margins. And the nice message here is that for the copula that is really true. So if x has distribution f and you have continuous margins, at least then, if then you have strictly increasing transformations for all j, then t1 of x1 up to td of xd has also copulas. So yeah, you were all nodding. Maybe you thought if we don't object, then we'll get faster to the coffee break. And yeah, it's still 5 minutes. So this seems a natural property. However, bear in mind, our favorite measure of dependence, linear correlation, does not have this property. For linear correlation, this is only true if the transformations are increasing and linear. So the correlation of x and y is not the same as the correlation, say, of e to the power of x and square root of y or something like that. The copula would have this property. And this already tells us something about the potential weak points of correlations, namely that is a dependence measure that is not margin-free, because if you have different margins but the same sort of dependence structure, you can transform these margins into each other by strictly increasing transformations, and that will potentially affect correlations. Copulas do have this property, which is sort of very nice. This interpretation of Scarcity Theorem, and I think most of it already said, the first part allows us to decompose any f into margins and copula, and so we can study dependence independently of the margins, because we may only have to look at this random vector u here. And And the second part allows us to construct flexible multivariate distributions with given margins.
Could you construct that uses something different than uniform margins?
Well, yes, of course, you could say, I want to standardize everything to have normal margins. Then you would, you can call this whatever copula is already gone as a name. You can call this normal normula. The reason why one does the uniform margins is the convenience for simulation in the second part, because then you just have to apply quantile transforms. Otherwise, you could work with normulas if you wanted to.
But also Fresher in the 40s was one of the early contributors. You will see his name on a couple of slides. I think his early work was on a uniform distribution minus a third, something like that. Yeah. In extreme value theory, you very often get easy result of multivariate extremes, which I didn't do, if you transform your margins to something called the unit Fresher distribution. You saw the Fresher before. Yeah. So it's a very good question. Depending on the kind of theory you're looking at, there's sort of the easiest margins to discuss a thing. As Rudiger said, by now it's absolutely standard to transform the copula to the uniform margins. But on uniform margins, you can put a copula on any margin. On the uniform margins, they all look the same.
Yeah, for graphical analysis,
if you put them on the normal margins,
you see differences.
Structures,
yeah.
the same copula.
Normulas would be better.
Yeah, I think, but the standard theory, because of the simulation, start with the uniform margin. Okay. Absolutely standard. Okay.
Good. Well, since I will not finish my theoretical slides before. Welcome back. Well, I'd say those of you who are still here perhaps have the endurance to do triathlon. Good. So in last hour, the good news is today we stop at 5. Before the break, I explained to you Scarcity Theorem with its 2 parts. The first one, how to construct the copula from a multivariate distribution, and the second one, how to construct a model with a given copula and given margins. And we're going to look at a few pictures where we do that. So, and we're also going to generate a few of these things. On the left picture here, you see a scatter plot of 1,000 samples from a bivariate normal distribution. A normal distributed mean 0, and correlation or covariance matrix is the same, is already standardized, equal to P, and P is given here a correlation of 0.7. And good, there are 3 points A, B, and C. C is blue, B is red, and A is green. And what we're going to do now is we're going to construct the corresponding Gauss copula. Or realizations from the corresponding Gauss copula. How do we do that? Well, very simple. We apply the probability transform. So in this case, the marginals are standard normal. So we apply the standard normal distribution to each of these points. And in particular, the point B here, the red one, goes over here. The point C ends up over here. And the point A happens to end up in the upper right corner. And then these plots here are realizations from the corresponding copula, which is called the Gauss copula because it has been constructed from the multivariate normal or multivariate Gauss distribution. Good. What you already see from this picture, this comes back to your question, is that if you look at this if you look at these points on the right-hand picture, you don't see much structure somehow. You would have to use different scales or different margins to see more. Still, that's the copula we have. The second part of Scarcity Theorem that also answers why, even if you don't see much, we're still convenient to stick to the univariate margins. On the left picture, we see the same Gauss scatter plot as before, but now, say we're in the credit application and we want to construct a realization of the lifetime of 2 companies, or the default time of 2 companies, tau 1, tau 2. Each of them are individually exponentially distributed, and their joint distribution is described by the Gauss copula. If you think that this is a weird idea, you're not alone, but that's the Gauss copula model which people claim has destroyed Wall Street. So beware. And now, once again, our points A, B, and C. And these are now the scatter plots of waiting times. Well, it doesn't look too unreasonable. At least both of them are positive. And that's the realization. It corresponds to the copula B. The C1 is blue down here. And the A1 is this one. Good. So that's how these two parts of Scarcity theorem work.
So you take the inverse transform now.
Yeah, now I'm taking the quantile transform, of course, to go from 0, 1, in this case to R plus, because it's a distribution on R plus. We have another picture there. We're going to generate one live in a few minutes, so that's why I'm going to jump over these slides. This one or the next one? This slide or the next one?
Yeah, this one. Yes. So on the left you get some distribution.
On the left we have some distribution. In this case it's a normal distribution.
Yes. Then you count something which
That's a T distribution.
Yeah, now you go from the to another distribution.
Exactly.
The left-hand side is in this case the multivariate. Go back to the Gaussian. Go back to the Gaussian.
Let's go to the one which we had.
Yeah, you stop the bivariate Gaussian. You transform the margins to uniform margins. These are increasing transformations. The two have the same copula. That's the Gaussian copula. They have the same copula. They're increasing. And now the same copula, different margins. It's increasing transformation. Now you go back to the next picture. You repeat the picture. You have your copula on the left, and now you put that copula on exponential margins. Again, you use the quantile transform, increasing. The two pictures of the same copula, but now you have exponential margins.
Of course, you could do the whole thing also the other way around. If you have this artificial distribution over there, and if you want to understand the copula that underlies it, you have to look at the margins, which are exponential in this case. You apply the distribution function of the exponential to each of these components. That gets you back to these copula data. That's how the thing sort of works. So essentially, this is very often it's a concatenation of probability and quantile transforms. Good. So that's the same story with the T distribution. And now we come to Fréchet-Höfting bounds. Fréchet was already mentioned here. These are two bounds, numbers between which every copula must lie. These bounds are interesting because they do correspond for a number of reasons. On the one hand, we can use them to derive later on bounds on linear correlations, bounds on distribution functions, and they are also themselves copulas, at least the upper bound, which arise as certain extreme cases also in optimization problems when you look for worst case risk measures. Not necessarily value at risk, but other ones. Good. So for any d-dimensional copula C, it holds that W of u is smaller than C of u and bigger or equal to M of u, where M of u is the minimum of all these components, and W of u is the maximum of 0, and the sum uj minus d plus 1. The upper bound M is a copula for all d. And it is a very simple distribution function. It's the distribution of the random vector. And that's the wrong one. This one. It's on the slide, okay. Yeah. Sorry, it's the distribution function of the random vector u. So you take a uniform random variable u, and you just stack it d times, and then you get a random vector, even if it's a very boring one, and its distribution function is just m. So in the two-dimensional case, if you just have 0, 1 here, this distribution function would just live here on the diagonal because both components always take the same value. The W in the two-dimensional case is also a distribution function. It's a distribution of u and 1 minus u. If u is uniform, then 1 minus u is uniform as well. And so the other one would live on the off diagonal. So that's where the W lives, and that's where the M lives. This W construction somehow works only in 2 dimensions. U, 1 minus u, 1 minus u is again u, whereas the other one works in any dimension. Anyhow, both W and M do give us bounds on copulas, and these bounds are also sharp in the sense that you can come arbitrarily close, but the upper bound is always attained, the lower bound only in 2 dimensions. Here you see the corresponding plots of these distribution functions. When they are sort of the most extreme situations, every copula you can think of must lie between these two. Thank you. Must lie between these two graphs here. One doesn't see very much. One sees a little bit more when you look at the level lines of the distribution function, but I think these plots have now gone just to the book. There's also an interpretation of that when you want to understand which type of dependence structure is described by these two bounds. The upper bound W and upper bound M describes perfect dependence. Perfect dependence means that all sort of components go in the same direction, or if you want perfect dependence or comonotonicity, as you call it, so that's great. If you play Scrabble and have too many O's, then you use the word comonotonic. And perfect dependence means essentially that x is a random vector, x1 up to xd, and all the xi of the form v of, say, y, for y a one-dimensional random variable, and v increasing. So this is really a situation if you have a random vector whose distribution is described by this upper bound, or the so-called vi, sorry, yeah. By the upper bound x. But it's 1y, that is important.
That's important.
It's one, thank you. It's one. That is perfect dependence. It's easier maybe understood from this than from the copula itself, but this is equivalent. Xi is vi of y, so they are really, it's a one-dimensional situation. If you know the y, you know all the x's, and they are also all moving into the same direction because the v is strictly increasing. I mean, you could, of course, also have all v strictly decreasing. That would also work. You just can make them increasing by putting a minus in here. And if you have such a situation, that is the case where you have the corresponding random vector has this copula M, and that's therefore called perfect dependence or comonotonicity. Good. It's time to give you some examples of copulas. If you want to classify the way of constructing examples, you have 3 ways. You can say there are some fundamental copulas which describe special dependence structures. Implicit copulas, they are extracted from known multivariate distributions via Scarcity Theorem. Explicit copulas, these are copulas where you write down closed form expressions, even if, strictly speaking, most of the time you also have probabilistic construction. Good, the fundamental copulas, which fundamental ways of dependence could there be? Well, one thing is if you have 2 random variables and they have nothing to do with each other, then they're independent. That is a special dependence structure. Another one is this one here. They could be perfectly dependent or move in the same direction, comonotonicity. And in two-dimensional case, they could also always move in opposite directions. So that is counter-monotonicity. I'm highlighting d equals 2, otherwise it doesn't work. And then we have that x1 is equal to v1 of y, and v1 is increasing, and x2 is v2 of y, and v2 is decreasing. So they go in the opposite direction, and this counter monotonicity, that's the copula W. This would be the three sort of special dependence structure: independence, counter monotonicity, and comonotonicity. The other example, the implicit copulas. These are copulas that arise from well-known distributions. Now, a nice class to start with, which we understand well. Maybe not the distribution function, but the density and all its general behavior, are the elliptical distributions, which Paul and Marius introduced this morning. And we can construct the corresponding copula via Scarcity Theorem. But now you should know what we have to do. We start from the multivariate distribution and apply the probability transform. And the nice thing about this elliptical, one of the nice things about these elliptical distributions is, of course, the fact that the marginal distributions also belong always to the same class. So we sort of know which probability transform we have to apply. The first case in point is the Gauss copula. That is when we do the whole thing with a normal distribution. So we start from a normal vector x with mean 0 and correlation matrix P. Well, a question, but at this point of the day, I shouldn't ask you any questions anymore unless if I'm willing to answer them myself. So why is it that it's enough? When you remember, those of you who studied math remember this WLOG, which always means why on earth can I assume that? In this case, why it's enough to consider normal distributions with mean 0 and covariance matrix P. The point is the copula of a random vector is invariant under strictly increasing transformations. Centering and standardizing are increasing transformations. So if I take a general random vector or one which has been centered and standardized component-wise, the corresponding copula remains the same. So I may sort of take the centered and standardized one as representing the whole equivalence class of copulas, if you want. So that's why this is without loss of generality. We take a normal random vector, and the Gauss copula is given analytically by taking the multivariate Gaussian distribution function corresponding to the correlation matrix P, phi P of phi minus 1 of U1 up phi minus 1 of UD, because the margins are uniformly normal. That's a nice way of writing it down. It's of course not very useful because we don't know the multivariate distribution function. But what we would know is the density, and we would know how to sample from this copula, for instance. Some special cases. Good. If we take for the correlation matrix the identity, then we obtain the independence copula. Why? Well, if we have multivariate normal random variables which are uncorrelated, then basically then they're independent, and we've learned that this conclusion is correct for the normal distribution and essentially only for the normal distribution. If we take P to the correlation matrix, which consists only of 1, so all correlations are 1, then the corresponding Gaussian random vector just means we take one random variable, standard normally distributed, and stack it d times. And the corresponding copula is going to be the comonotonicity copula, so that gives us the upper free sheet bound. And if you take a two-dimensional situation and if you take correlations -1, then we get the lower free sheet bound. While we do not know the copula itself because we do not know the multivariate distribution function explicitly, we do know the density simply by taking d times the derivative of the multivariate distribution function, and because we know sort of it has a nice explicit formula which is given here. This is relevant on the one hand for plotting, and maybe more importantly, if you really want to fit copulas via maximum likelihood, you need the likelihood function, and for that you need the density. That can be done in this case, but I think for reasons of time, I'm not going to do into this in particular. Good. The thing can be done with the normal distribution, with a multivariate one that gives the Gauss copula. The thing can be done with the t distribution, and not surprisingly, this gives the t copula. Again, we may center, and again, we may take the dispersion matrix to be a correlation matrix. We have one additional parameter now, the degree of freedom parameter nu. This will not go away by clever transformations. That is a very crucial part of this copula. And we have the copula family as before, and we have the density as before. Special cases, if we take all components to be perfectly correlated, then we're still in we get the comonotonicity copula, we're still in a one-dimensional situation. But be careful, if we take the correlation matrix to be the identity, we do not get the independence copula. Why? Yes, exactly. We've learned this morning that if you take a normal mixture model other than the Gaussian as a T, and then you cannot make this conclusion that uncorrelatedness implies independence. So basically the only multivariate normal mixture where this is possible is the Gaussian case. And T is not Gaussian unless if nu is infinity. And so in this case, the components are not independent for if they are uncorrelated. And so the correlation matrix is not and hence the copula is not the independence copula. In the two-dimensional case, if you have them perfectly negatively correlated, you still get the lower free sheet bound, the counter-monotonicity copula. Using Scarcity Theorem and the explicit form of the multivariate T density, you can write down the density of the multivariate T distribution as well. That is this formula. If you want to understand everything about the multivariate T copula, you have to read an old paper by Alex and a PhD student of his. Note the difference. Okay, we come to this later. These two copulas are different, and the main difference is that the T copula has more mass in the joint tails. But I don't want to say too much about this now, because otherwise I'm taking too much away from the continuation of the copula treatment on Thursday morning. Good, here you just see the plots of the corresponding densities and advantages, drawbacks of elliptical copulas. You have the density, they're relatively flexible, you know how to sample them. You do not have an explicit form of the copula function, and they have the same behavior in the upper and the lower tail. Good, to wrap this up, let's do a little bit of R before Alex concludes today. Which one is it, this one? Yeah, okay. Good. Alex is just, thank you. It's a script which is also on QRM tutorial. It is a, I have to move up here. Good. It's by Marius and Alexander, and it's a copula basics or something it is called. So if you want to play around with it yourself, feel free to do so. It generates and transforms multivariate data using probability and quantile transform. So we basically do once again live what we've done before. What we have done before on the slides. Just need a few libraries for this to work, and for reproducibility we set the C to be fixed. Good. So our first job is to sample from a bivariate normal distribution. I'm generating the corresponding correlation matrix. We're going to generate 1,000, be careful not to forget a line, 1,000 data points, and we're going to generate multivariate normal random variables, 1,000 of them, a vector with two-dimensional with this given correlation matrix with correlation 0.7. And we're going to plot this. That's what you're going to see here. That's simply the scatter plot from the multivariate normal distribution. We want the corresponding copula, so what we have to do is we have to apply the corresponding quantile transform. That's what the next command does. Use assigned p norm of x, the probability transform, sorry. We have to apply the corresponding probability transform. And we're going to see the corresponding scatter plot from the Gauss copula. You had this on the slides more or less. Now, the marginal distribution of this picture here should be uniform. So if you plot the histogram, it should bin all the data in both dimensions. It should look roughly like the histogram from a uniform distribution. We can check this. That's for the first component. Well, it's not perfect, but you need an awful lot of data before simulated histograms are perfect. It's just 1,000 points. Yeah. Okay, we can do the same thing for the other component as well if you want to. Good. Now what we're going to do next is we're going to take our sample from the Gaussian copula, and instead of transforming it to a random vector with exponentially margins, now we're going to transform it to one that has margins, standard T margins with degree of freedom equal to 3.5. Okay. The y, I'm now getting this new data by applying component by component the corresponding quantile transform of the univariate T with degrees of freedom equal to my nu. So let's do that, and let's plot the result. And we're going to plot in black the original. So what we have here in blue was just the plot of the artificial distribution with Gauss copula and T margins, and in black we had sort of the ones with the Gauss copula and normal margins. And because the T distribution has heavier tails, we're going to see more large points. That's why all these things out here, and it's hardly visible, are blue. That's the one that corresponds to this new model. Good. Okay, there's another example where we can do this with T copula and asymmetric margins, but in the interest of time, I hand over to Alex so that he can finish his multivariate distributions in time. and you can still enjoy a little bit the beautiful weather out there.
So, hello and welcome everyone to our second part on copulas this morning. I see everyone could kind of evade the maximum domain of traction of their beds this morning. That's fantastic. So what I would like to do is would like to do a little bit of a recap on copulas and then discuss more aspects around dependence models with copulas, of course. So first question for you. Can anybody tell me what is a copula? Yes, that's why I'm asking you. You already defined a copula. So repeat it in your own words. Explain it. What is a copula? A dependence function. Okay, that's not a very precise definition. Okay, a distribution function. Yes. Multivariate. A multivariate distribution function.
Restricted to a unit cube.
Restricted to the unit cube, that still doesn't make it unique. Uniform margins, that's still not 100% correct. What type of uniform margins? 0 and 1. Standard uniform. See how difficult that is. That one line already. So a copula C is a multivariate distribution function with standard uniform univariate margins. Yeah? That's important. And this is a stochastic definition, essentially, a probabilistic definition. You can use the characterization you already discussed as an analytic definition, if you like. So if you just view C as an analytic function, then it's a mapping from the unit hypercube to 0, 1, which is grounded. So if one of the components is 0, you will get 0. Which has standard uniform margins. This is this part here. Yeah? So if all components are 1 except one component, you get that one component back. And it's increasing in a very specific way. Yeah? So it's not sufficient that C is increasing component-wise only. It has to be overall a distribution function. So this is what's hidden in here. Yeah? So the de-increasingness is directly related to having a multivariate distribution function. Now forget about this formula. That's very tricky. Yeah? But in case the C is differentiable with respect to each component, I have a density. And what this property essentially means, this type of increasingness, is that my density or density candidate is non-negative. Yeah? And therefore, indeed, a proper density. Don't have to check the normalization because that's already contained in the first two parts. Yeah? So this is quite tricky in the analytic world, but in the probabilistic, in the stochastic world, if you like, it's a one-line definition, but still you have to get it right. And then how do I compute certain volumes, probabilities of falling into certain cubes? Yeah? So for that, I can use this formula I have to evaluate the copula at each of the endpoints of the cube I'm interested in, and then I can get the probability of falling in this hypercube, if you like, with these endpoints. Yeah? And always look at it in the bivariate case. You can write down the formulas, and then also look at it in the special case, the univariate case, and ask yourself whether it makes sense. Yeah? So in the univariate case, if I'm interested in the probability of a uniform to lie in an interval with endpoints A1 and B1, then what do? I evaluate the distribution function here minus here, so that's simply B1 minus A1 in this case, so I get the length of this interval. And this is in one dimension. And of course, I have to do that in the second dimension, probably in the third dimension, and so on. So in D dimensions, I have 2 to the D many corners of these hypercubes. And this is already a theoretical challenge, if you like. Course of dimensionality is a notion that's related to that. So if you want to compute the probability of falling of your, let's say, 200-dimensional vector of risk factor changes to fall in a certain, where each component falls in a certain interval, yeah? So then you essentially have to evaluate this formula in 200 dimensions. Yeah? If you make it slightly larger, about 260 dimensions, the number of corners of this hypercube is roughly the same as the number of atoms in the universe. So there's no chance you can do that. And
10 to the 85. 10 to the 85.
Yeah, 10 to the 85 roughly. Yeah? And there's an R script online in the very first chapter that essentially computes this formula in larger and larger dimensions, so over 2 to the d many corners, just for the simplest copula you can look at, namely the independence copula. There I know, of course, I just take the length of these intervals, and the volume is then simply the product of these lengths. And I compute this product on the one side. On the other side, I use this formula to compute this very same volume, and I look at the error between the two. Yeah? And you see how fast that's increasing in D. Yeah? It's also a very nice application of parallel computing. That's why it's done in the first chapter. Yeah? And this is in this very simple case that you have a very explicit copula, the independence copula. It doesn't get any nicer. Yeah? So if you cannot explicitly evaluate your C, then you have much more problems. The error is increasing much more. Yeah? And 260 is not that large. Yeah? We talked about portfolios of the size of 1,000, for example. Yeah? So there's absolutely no chance you would be able to evaluate this formula and get a proper probability. Numerically, what's happening is very soon you lie below 0 or above 1, you don't even get a proper probability anymore. Yeah? So you need different techniques to deal with that. Yeah? But theoretically, this is what's happening. And we interpret this cube, well, we interpret this volume as the probability of a random vector u following C to fall in this little cube. That's the idea. Now, why do we look at the unit hypercube? It was a bit the same as we studied in section 6 with the spherical distributions. My data doesn't look marginally uniform, so but why do we look at that? And how can we go from the space, from RD essentially, where my data lives, to the unit hypercube? And there are two transformations that are important. Both have already been on the board before, possibly several times. So the first one tells me how to go from the X space, I call it, where my data lives, to the U space, to the unit hypercube. So all I'm doing is I'm applying marginally to each of my components xj the corresponding distribution function, and then I know I get a uniform distribution. Slight assumption here is that, well, f has to be continuous. If f is not continuous, if f had a jump, I would simply not reach all values in 0, 1, can therefore not be uniformly distributed on 0, 1. So there I need continuity. That was also the underlying assumption of the first part of Scarcity Theorem, to recover a unique copula, if you like. And so that's mainly our assumption here, that our margins are all continuous. Now, this is going from the X space to the U space. How can I go from the U space to the X space? Let's say I know something about the copulas and I want to sample from a multivariate model with that copula and certain margins. So I need to go back. And for that, the quantile transformation is important. And now you see a little bit why I already mentioned that for sampling from the normal distribution. We already discussed this on the board. So I start with a uniform. I start in my unit hypercube, if you like, if I do that d times. And then I apply marginally the quantile transformation, and I then have my specific marginal distribution functions I specified. So very important two transformations. Both are univariate, and they help me applying these concepts marginally to go from the X space to the U space and to go from the U space to the X space. And those transformations are used all the time, and they are also very nicely contained in the proof of Scarcity Theorem. So for the first direction, you start in the X space, so to say. You start with a multivariate distribution function, and you decompose it into a copula and the marginal distribution functions. There, the proof used exactly the probability transformation. Yeah? So you start from your axis, you want marginally the U's, you want to recover the copula essentially and the margins. So there you use the probability transformation. And for the second part, you use the same equality here essentially. You just read it the other way. You start on the right side, you have specified a copula, you have specific marginal distribution functions, you put them together and you get a proper multivariate distribution function. Yeah, so if I know how to, let's say, generate a sample from a certain copula, let's say the independence copula, for example, or the Gauss copula, then I can put on top simply my desired margins, yeah, so my margin with my marginal quantile transformations, and get a sample from the corresponding multivariate distribution function. Yeah. So extremely powerful two results that tell us how to go from the X to the U space and from the U to the X space. And Scarcity Theorem is of course probably the biggest theorem in this chapter, but it's really just this equality to keep in mind. Yeah? So if you have this equation here and you start reading it from the left side to the right side, this is the first part essentially. So you recover the copula, you decompose your F into the copula and the margins. Yeah? Or the second part then goes the other way around. You start from the copula, you plug in the margins you have, and you get a proper multivariate distribution function. Yeah, so you can read off this equation both directions, both parts of Scarcity Theorem. So it's an extremely powerful result. Yeah, so this plus the Fréchet-Höfting bounds plus the invariance principle. If you have these three theorems in your pocket, yeah, to use the same idea as Paul used in 5. If you have these three ideas, notions and theorems in your pockets, then you can tackle a lot of dependence problems. And what we will also do later in chapter 8 is essentially we have, for example, a lot of information on the marginal distributions, but we have only little information about the copula or possibly no information about the copula. And then we do things like studying the class of all multivariate distribution functions under these specific margins, but maybe no information of the copula. So you can play with this equation. You can also play with it in the other way around and say, hey, maybe I know exactly the copula, but I don't know the margins, so I get a whole class of distribution functions with that specific copula under all sorts of margins. Yeah? So you can keep essentially one fixed and treat the others as unknown, and then you get whole classes of distribution functions you can study. Now, what you can easily derive from this equation is if you substitute the x's, if you put in F inverse of u's, then the F and F inverse cancel out, so you write the copula as F of your multivariate F, and then you plug in the marginal quantiles at U1 to UD. So this is then essentially the form of the copula itself. The U's are in the unit hypercube. Yeah? So all the U's are in SIL1. And this is, of course, helpful for constructing copulas like the Gauss copula, the T copula, these implicit copulas. Yeah? So if you already know the multivariate distribution, you can derive from that the corresponding marginal distribution functions. You compute the marginal quantile functions from that, you plug them in, you recover a copula. And that's something you can do in general. Yeah? If you encounter a new multivariate distribution function, or let's say a stochastic representation, we had the normal variance mixtures that Paul explained. Yeah? So here you have a new stochastic representation. Try and write down the multivariate distribution function. From there, derive the marginal distribution functions, invert them to get the quantile functions, plug them in, and you have the corresponding underlying copula that contains the dependence between the components of your random vector x. Yeah? So it's an extremely powerful result. Also, what you immediately get from here is the copula density in terms of the density of that multivariate distribution function. Yeah? So the density of the Gauss copula, the density of the T copula, for example, you immediately get from here. Yeah? So all you need to do is as usual, yeah, multivariate density, what do we need to do? We need to differentiate this function with respect to each component once. So if I do that, what I actually get the derivative of f with respect to each component once. That's, of course, my little f, my density of the multivariate normal, let's say, my density of the multivariate t. That's explicitly available. And then from the inner derivatives, I get the derivatives. Each time I differentiate, I get the derivatives of these quantile functions, which are essentially 1 over the derivatives of the functions evaluated at the quantile functions. The formula itself will appear later. Just want to show you here already what you can derive from essentially this equation. Yeah? So always keep this equation in mind. Good. So the proof you already discussed, applying the probability and the probability transformation and quantile transformation. And and then there's a bit of wording here. So a copula model for X means essentially that we study a parametric model for C and for all of the margins. Yeah, so for example, my copula could have 1 parameter I'm interested in, and my marginals could have 2 parameters each, for example. Yeah? So then I would say, okay, I have a copula model for X if I specified the distribution function of X through a copula and the margins, and both are parametric. Yeah? That's more important for estimation. We don't treat that too much, but I will come back to that later. Good, and then also saying that X following F fulfills this property is a bit cumbersome. So what you, one way of putting it is saying that X has copula C if the distribution function of F can be decomposed into C and the margins by a Scarcity theorem. Yeah? So this is just saying X or F has copula C if the equation by Scarcity theorem holds the decomposition, with copula C being the C and the margins F1 to Fd. Good, and then you discuss the invariance principle. So that means if I start from a random vector X and it has a certain copula C underlying, and I transform each of the margins possibly with a strictly increasing transformation, then that means the corresponding new random vector, namely this transformed random vector, call it Y, for example, of course also has, by Scarcity theorem, a decomposition into a copula and the corresponding margins. The margins are, of course, different than the ones, possibly different than the ones of X, because I transformed them. But since all of these transformations marginally are strictly increasing, the underlying copula of my new random vector Y is actually the same as the one I started with X. Yeah? So that same copula as X has. Yeah? And this is extremely important result. So for example, from a statistical point of view, these t's can be my marginal distribution functions of x1 to xt estimated even. Yeah? So that means I have some data x, and I'm allowed, according to this principle, to study the underlying copula, the dependence between the components of x, by first transforming my components with their corresponding marginal distribution functions. Yeah? And then what do I get? I get a sample which has standard uniform univariate margins by the probability transformation. Yeah? But the copula did not change. So the copula is actually the distribution function of this new sample. And here I suddenly have a sample from this underlying copula. Yeah? And then, of course, I can make it visible. I can study it, study properties. I can fit models, and so on. Yeah? So the dependence doesn't change if I apply marginally strictly increasing transformations. Yeah? Strictly increasing, they have to be strictly increasing at least on the range of these x's. Yeah? So where x doesn't put mass at, I'm not interested in, yeah? in the transformation. Yeah? So for example, if I have, let's say the x's are already 0, 1, yeah? and I apply the sign to one of them, yeah? then the sign is increasing on 0, 1. So I know the new transformed sample will still have the same underlying copula. And that's important because if the copula would change by such a transformation, then I could not first estimate the margins and then make construct this sample from the underlying copula. Because by applying these marginal distribution functions, I would have changed the underlying dependence. But this principle says no, the underlying dependence does not change. And this gives us a very simple way of constructing a so-called pseudo-sample of the underlying copula. They are also called pseudo-observations. So they are not observations we make directly because we only observe the x's, remember the x space, but we can easily, by first estimating the marginal distribution functions, recover the u's that follow C, so a pseudo-sample following the underlying copula by this transformation. And then we can plot that and so on. Yeah? So extremely powerful. And yeah. Okay, so this was the invariance principle. And then visually, what's happening is the following. So you already discussed this as well, but I just want to quickly point out some things here. So here you start with a sample from a bivariate normal distribution, a certain correlation given. And now this is in my X space, right? This is my multivariate normal distribution sample here. And I color 3 points, and you see in each direction how they are ordered. So according to the x-axis, first comes B, then C, then A. According to the y-axis, first comes C, then B, then A. And then I transform that sample marginally with the corresponding distribution functions. So I know the marginal distribution functions, what are they? They are the standard normal distribution functions. So I marginally apply the standard normal distribution functions, and then I get this sample. And this is the pseudo-sample, the pseudo-observations of the underlying copula. So I really see the underlying dependence, the dependence underlying this sample in this sample. So this is the sample from the underlying copula, from the Gauss copula. And now what do I see where these points are mapped? So if I go along the x-axis, first comes B, then C, then A. If I go along the y-axis, first comes C, then B, then A. Exactly as before. So what's happening by applying marginally strictly increasing transformations, which by normal margins, standard normal distribution function is, I only change the values here, but I do not change the ranking between the points. So it's not that according to one of the x's, suddenly, let's say C lies before B. So I do not change the ranks. So essentially, this is also what you can do non-parametrically. If you do not want to assume that your margin is standard normal here, then you simply rank the data and divide by the sample size, for example. So this is extremely easy to do. So you just look at the ranks, essentially, the scaled ranks of your data. Yes, of course.
Why do you think that the right feature is better than the left one?
Good point. Very good question. Why do you think the right picture is better than the left? Okay, so let me go to the next slide. So here you see the same sample from the underlying Gauss copula as was before on the right-hand side. And then, once I study that sample, let's say I fitted a copula or thought about an interesting model for this, then I can go back to my X space and say, okay, I put different marginal distribution functions on top. And we are just playing here. It has nothing to do with real data yet. We're just playing here. But what I can do is, of course, I can apply any marginal quantile functions I like on top of this copula sample. So this is now going in the second part of Scarcity theorem. This was the first part, going from the X space to the U space. Now I go from the U space to the X space. So now, this is now the second part of Scarcity theorem. And the marginals I chose here are exponential. Now I can make this a bit more drastic. So I can put all of the samples in the lower left corner if you like. Because what you see in this picture and what you see in this picture are two things at the same time. You see the dependence plus the marginal information. And actually you mostly see, and this is the story here, you mostly see the marginal information. Yeah? For example, here I would expect, from this picture, I would expect that my underlying copula sample has similar concentration of points here as up here. Yeah, that I would believe. I see a symmetry with respect to the secondary diagonal. I would believe that this remains here. Yeah? Now, if I show you just this picture, would I believe that this is the underlying copula? No, I would say there's a much higher concentration of points here than up here. Yeah? So the human eye is very much distracted by the marginal information here. But we are interested mostly in the dependence. So you see how incredibly dangerous it can be to study dependence by looking at this picture instead of that, by looking at this picture instead of that. And I normally start my copula course by showing just this picture and showing just that picture and ask the students, where do you believe the dependence is larger? And most say, oh yeah, here you have a clustering of points going on. There's much more dependence here, concentration of points. Some even see some linearity here, yeah, so high correlation. Yeah. That's ridiculous. The underlying copula is exactly the same. And I chose exactly the same sample here. It's not only the same in distribution, it's the same surely, if you like. Yeah. It's exactly the same. So, yeah, so you see that how important it is to extract that sample for studying dependence. Yeah. Now, question for you. Why didn't I start with the general bivariate normal distribution here? Why did I start with mean vector 0 and correlation matrix rho? Covariance matrix being a correlation matrix. Why didn't I start with a normal with mu and sigma here? Yeah, very good. Why? It would be the same copula. You wouldn't get anything new. Why? Very good. Yeah, marginally to go from the normal with mu and sigma to the normal with 0 and rho. Yeah, all you do is marginally a location scale transform. And that's increasing, yeah, in this case. This is an increasing transformation component-wise. And therefore, by the invariance principle, right, by the invariance principle, the underlying copula remains the same. I would not get anything new. Yeah, so here's the invariance principle. Very nice. Good, and you can do the same for the t-distribution. If you make the underlying copula sample visible, then you see a higher concentration of points, slightly higher concentration of points, but it's actually not so easy to see. You could even expect to have a concentration of points in the corners here. That we will try and quantify, put into a number later. That's the notion of tail dependence. Good. Then the third most important result in this chapter are the Frechet-Höfting bounds that tell us that every copula is bounded in between these two bounds. The lower Frechet-Höfting bound W, which is in the bivariate case U1 plus U2 minus 1 and 0, the max of the two, and the upper Frechet-Höfting bound, which is simply the minimum of the two components. Yeah? And these bounds will be extremely important later when we study how useful the linear correlation coefficient, Pearson's correlation coefficient, is when quantifying dependence, when putting when summarizing the whole dependence contained in the copula by a single number. Yeah? Good, so we will come back to that. But let me already stress the stochastic side here. Yeah? So what are stochastic representations for these extreme copulas W and M? Careful, W is only a copula in the bivariate case. So here are the stochastic representations, and those are very easy calculations you should really do. So the way this works is that I take the very same standard uniform random variable, and I put that into a vector, and that turns out to be distributed as the upper Frechet-Höfting bound. One line proof. Yeah? So the probability that the u's are less than or equal to u1 to ud is, because it's the same u, the probability that the u is less than or equal to the minimum of my components. The u is standard uniform, so I get the minimum of my components. That's this part here. Yeah? So they are very simple proofs, but stochastically they tell us a lot. So they tell us that the upper Frechet-Höfting bound is actually the strongest possible positive dependence I can get. Because if you tell me what the first component is, I know with probability 1 what the second component is. It's the same u. And it actually doesn't have to be the same u, but in this very special case that we look at the corresponding copula, it is the very same u. So if you give me the first coordinate, I can say with probability 1 already what the second coordinate is. That's different than here. If you give me the first coordinate, I can only, well, there are still a lot of choices here, yeah, so to speak, but not for the upper Frescher-Höfting bound. So this is why this is the copula model for the strongest possible positive dependence. Yeah? Then for W, for the lower Frescher-Höfting bound, you'd simply say take u, and in the second component, 1 minus u, well, with the very same u. So again, if you tell me the first component, I know with probability 1 what the second component is. Yeah, so very strong dependence again, strongest possible dependence again, but here in the negative sense. Why in the negative sense? Because if the first component is increasing, goes up, the second component is decreasing, goes down. So the strongest possible negative dependence. That's modeled by the lower Frescher-Höfting bound. Yeah, and this also already on the stochastic side essentially tells you that W is cannot be a copula in more than 2 dimensions. Because if my first component goes up, my second component goes down with probability 1, what should my other components do? There's no unique notion of a perfect negative dependence there. Whereas in the positive dependent case, if one component goes up, all other components have to go up as well. That's the strongest possible positive dependence you can have. Yeah, so there's a lot contained in these stochastic representations of these copulas. Yeah. Those will be theorems later that, of course, tell you, okay, if you have two random variables and one is with probability 1 an increasing function in the other one, then you have the upper Frescher-Höfting bound as underlying copula. Yeah, so you can generalize that, but you already see these kind of results from here. Good. Then the 2 Frescher-Höfting bounds are the only copulas that you can actually easily draw as distribution functions. Yeah? At least, of course, in the bivariate case. So this is W as a function in U1, U2. This is the upper Frescher-Höfting bound M, and you essentially see in both cases you have 2 planes intersecting. Yeah? And you have a kink here, and that kink always relates to this very strong dependence, if you like, in a certain sense. Yeah? We'll have an example later on that as well, but yeah. So, and here these are 2 good cases to go back to this notion of computing volumes to falling in certain cubes, because you can do them manually here, essentially. So if I take a small cube down here, then the probability of my u falling in this little rectangle I would need to evaluate the corresponding copula, the W, at all 4 corners. Yeah? At all 4 corners, it's 0, so the probability to fall in here is 0. Now I go back to the stochastic representation. That tells me that the mass is only put at like this. Let me just use the board. So if I have the unit square here, then u and 1 minus u, if I have some realizations here, standard uniform, then 1 minus u puts me essentially here. So my whole mass is put here, and this part you essentially see down here in the unit square. Yeah? So you see exactly where the copula has a kink, it puts mass at. And the small rectangle I asked you is exactly lying here, let's say. And the copula, well, what's the probability of falling in here? If all the realizations are here, it's 0. Yeah? So you get that from the stochastic representation, and you get that from the analytic formula. You can do the same exercise up here. Interestingly, you will also see that it's 0 probability, which is even more immediate from the stochastic representation. Yeah, so you can do these tricks here, and one of the rare cases where you actually see something from the copula. As in the univariate case, we do not look at or study the distribution functions themselves. We study densities, for example. Yeah? We see much more shapes in the density, so it's a bit the same in the multivariate case. Good. So the Frescher-Höfting bounds, and then you started looking at examples of copulas. So there are so-called fundamental examples, very special cases that have very strong meaning for the underlying dependence. There are implicit copulas. Those are the ones that are constructed from Scarcity Theorem. Yeah? So you start with already known multivariate distribution function, for example, the ones we've seen in Chapter 6, and you recover the copula from them. And then there are explicit copulas that essentially already construct copulas directly without any underlying multivariate distribution function, or at least classically. And so those are different kind of constructions. As fundamental copulas, we have to mention the independence copula. So that's the one that corresponds to independence. So under independence, you learned in the beginning of Chapter 6 from Paul that multivariate F is simply the product of the margins. And that relates by Scarcity Theorem, of course, C of F1 to Fd being the product. That can only happen if C is the product of the components. So very simple copula. The density in this case you would get by differentiating with respect to each component once, which is very easy. So for each component would be replaced by 1, so your density is constant 1 over the unit hypercube in this case. And random variables x1 to xd, that as a joint distribution function have copula C underlying, so joint distribution function can be decomposed into C, are independent if and only if the underlying copula is the independence copula. The Fréchet-Höfting bound W is also known as the counter monotonicity copula. Counter monotonicity because the components walk in different directions. And mapping those to general margins, to x1s and x2, then relates to perfect negative dependence, as we already studied with the U1, U2. One component goes up, the other one goes down with probability 1. So if x1, x2 are perfectly negatively dependent, their underlying copula is W. And the same for very similar for the upper Fréchet-Höfting bound, but there you can have D components as before, and the D components are perfectly positively dependent if their underlying copula is the upper Fréchet-Höfting bound. So marginally I can do whatever, but if all my random variables move in the same direction, then I have underlying this very strong dependence given by the upper Fréchet-Höfting bound. Implicit copulas, the most important class of implicit copulas, most important class of copulas, if you like as well, are elliptical copulas. Those are the copulas constructed from the elliptical distributions. The normal variance mixtures as a subclass are the most important examples. So our multivariate normal, our multivariate T distribution, we start with those give us the Fs. And then marginally, we know we have standard normal margins, we have T margins. We can apply the marginal distribution functions to get the corresponding copulas, the Gauss and the T copula. And you see here, there's not so much we can actually do in writing down this copula. This looks as Scarcity Theorem, if you like. You have the F here, and the F inverses the margin, the Fj inverses the marginal quantile functions in here. But for the normal, the multivariate normal, there's not so much we can do explicitly, and the normal quantile functions neither. So it's a very implicit construction, the construction implicitly given by Scarcity Theorem. And something important to note here is that if you want to evaluate that for computing the probabilities of falling into cubes, for example, then this multivariate normal distribution function for d greater than 3 is evaluated by quasi Monte Carlo techniques. So this randomized quasi Monte Carlo techniques. And so you already have an error in computing these probabilities at each corner, and of course that can pile up quite quickly. So numerically, this is not so easy to tackle, to evaluate the copula explicitly. But the copula itself, for statistical purposes, we do not need so often. We rather need the density, for example. And the density that we already discussed before, that immediately is implied by Scarcity Theorem. You have a nice formula for that. In terms of the density of the underlying multivariate distribution function you started from to get the corresponding implicit copula. And for the multivariate normal, multivariate T distribution, you have the densities given explicitly, and therefore have explicit forms of the copula, quite explicit forms of the copula densities. So here you see your multivariate normal density, and then the correlation, the inverse of the correlation matrix in here, and that minus identity, that's the inverse of the correlation matrix under independence, of the normal under independence. Remember, multivariate normal distribution, independence equivalent to uncorrelatedness. And that's what you see here essentially. The density splits is given here as the product of the margin. So, so that corresponds for the normal to the uncorrelated case, and this is the inverse of the corresponding correlation matrix. So you see a little bit where this formula comes from. Good, and I can do the very same for the T copula. Again, because it's an implicit copula, there's not so much I can do. I can see more from here than essentially the general formula here. So my multivariate distribution is a T with new degrees of freedom, correlation matrix rho, and my marginals are univariate T, quantile functions here. Good. Again, we can have a density in this case. This looks a bit daunting, but it's actually extremely nice if you want to compute the log density for maximum likelihood estimation, for example. Then you have a lot of products in here and quotients and powers, and the log can be quite nicely computed based on that. There's one paper I want to point out here by Stefano De Marta and Alex. I think it's an extremely interesting paper to read about the T copula and related copulas, related constructions, also stressing stochastic representations and so on. Very nice paper to read if you want to know more about T copulas. Good. And the T copula, as you've already seen in the pictures, seems to put slightly more mass in the corners than the Gauss copula, but that we will make more precise later when we have the notion of tail dependence. Good, so here you have the corresponding densities, and they also reflect that you have more mass in the corners, in the lower left, the upper right corner for the T copula than for the normal. Be careful here, the scale is different, so there's really more mass here in the tails. And you see much more structure here from the densities than you would see from the copulas. From the copulas, normal or T copula, the copulas themselves, you don't see so much. I will look at more examples, go through more examples with you on the computer soon. But let me stress here, at least for the normal copula and the T copula, that the advantages are that you have a correlation matrix underlying as a matrix of parameters. That means you can adjust pairwise dependencies, so that's quite flexible. The density is available, which is great for fitting. And sampling is typically simple as well. So sampling is just sampling from your multivariate normal or multivariate T and using our probability transformations. So it's very easy to do that. In general, for elliptical distributions, sampling we discussed as well. We had a general stochastic representation, but to get the marginal distribution function, that's not always so easy. But for the multivariate normal, multivariate T, for the normal variance mixtures, that's typically easy. So then you can really compute the probability transformations and get samples from these copulas. Drawbacks, the C itself, because it's implicit, the C itself is not given explicitly. Computing probabilities then is a challenge. And radial symmetry is a drawback. So Frank recently said that I want to have more asymmetry. I see asymmetry in the BMW Siemens data. There was a higher concentration of points in the lower left corner than in the upper right corner. That you cannot capture by the normal or the T copula. So that means the radial symmetry means the symmetry with respect to the secondary diagonal here. What happens in the lower left corner happens with the same probability in the upper right corner. What happens with the lower left corner happens with the same probability in the upper right corner. Yes, question? Yes, that's XQT. Go to that paper. Yeah? You can do a lot of things here. Yeah? You can also put transformations on top of these basic building blocks of copulas we discussed. But as Paul likes to say, first start to walk before you can run. Yeah? There are many, many extensions available, transformations, Liebscher transformations, for example, to make all of that more flexible. Maybe mention a little bit more later. Good, and then as explicit copulas, we can study so-called Archimedean copulas. There you have a very explicit form of the copula. Yeah? So there already you can more easily compute probabilities, and that very specific form, very explicit form of the copula is given like that. You have a function, a so-called generator, psi, and as argument of this one-place function, you have the inverse of psi of u1 plus down to psi inverse of ud. So the thing to take away here is that the copula has this functional form, but it's essentially written in terms of just a one-place function, a univariate function. And that makes a lot of properties of these copulas can be derived in terms of this one-place function. That makes that very nice to use for computations and so on. Now this one-place function psi, it roughly looks like that. So you start in 0 at 1, and then that function psi goes down like this. And for t going to infinity, psi goes towards 0. Now, why do I have to start at 1 and 0, and why do I have to go down to 0 for t to infinity? Go back to the definition or characterization, if you like, very first slide on copulas, and think about that. Yeah? So if psi doesn't go towards 0, then of course my c cannot be grounded, for example. Yeah? So it's very easy to check. Yeah? So groundedness and uniform margins, you can typically easily check if you have the copula given. Yeah? The problem is the de-increasingness. Yeah? That you cannot easily write down a function that's de-increasing. Yeah? So indeed, then a proper distribution function. That's the problem. But and this is indeed a problem here, because for the first time, this was not derived from Scarcity Theorem, from a proper multivariate distribution function. I just give you this functional form. Why is that even a distribution function? That's not so easy to get, yeah? But one can show that this is a distribution function under certain assumptions on that generator psi. Yeah? For us, that generator will always be strict, yeah? So it will always be strictly greater than 0, but converge towards 0. Those are the classical examples, and in these cases, but again, there are extensions. In these cases, you can give a very explicit condition on psi for psi to generate a proper copula. And that explicit condition is that psi is a Laplace transform, yeah, of a distribution function on the positive real line. And this, again, makes this very easy to work with. Archimedean copulas are wonderful to work with because you have you can associate to any distribution function, univariate distribution function on the positive real line, Pareto, exponential, you can associate through the Laplace transform certain Archimedean copula. Yeah? And essentially, that can also be used for sampling to get a very quick sampling procedure. Good, what are examples of copulas that look like this? There's the Clayton copula, which has this functional form of the generator. There's the Gumbel copula, which has that functional form of the generator. The functional forms are not important. These generators roughly look like that. Yeah? What's important is the general form, and there are lots of examples available. And of course, they have different types of properties and so on. And I'll show you some examples on the computer later. So here you see a plot of a certain Clayton copula and the corresponding scatter plot. Now, again, as I stressed before, from the copula, you don't see very much. Yeah? So they all are grounded. Yeah? They all have uniform margins that you see here. Yeah? And the rest, I mean, they all lie in between the two Fréchet-Höfting bounds, so there's not so much you see. But from the sample, we see something new. So Frank should be happy now, because he has an asymmetric model now. Yeah? It's not restricted to radial symmetry. Yeah? So radially asymmetric sample. Yeah? So what happens down here seems to happen with a higher probability than what happens up here. So here you can model radial asymmetry. Now, maybe Frank is not so happy because there's still some kind of symmetry going on, namely the symmetry with respect to the diagonal itself. So what happens up in the top left corner happens with the same probability in the bottom right corner. So there's still this functional symmetry. So this is functional symmetry, symmetry with respect to the diagonal, and radial symmetry is the symmetry with respect to the secondary diagonal. Now, this functional symmetry, does it come as a surprise, or could we have maybe seen that immediately? Well, we have an explicit construction. So, of course, in here, functional symmetry means symmetry with respect to the two arguments. So C of U1, U2 is the same as C of U2, U1. And of course, in here I have a sum. I can permute the arguments. I will still get exactly the same outcome. So this functional symmetry is, of course, always there for Archimedean copulas that we already see as a drawback. Again, there are many extensions available, but overall, the Clayton, the Gumbel copula, they are functionally symmetric, the classical ones. And so that's certainly a drawback here.
Is it referred to as exchangeability?
Yes, it's also referred to as exchangeability. Yeah? Functional symmetry is also known as exchangeability, so you can exchange the arguments essentially. Yeah, so let's look at the density. So here you see the density of a Clayton copula, always just one, of course. Density and you see a high concentration of points in the lower left corner. Now, again, go back and let's check from the random sample whether this makes sense. I see this high concentration of points in the lower left corner. So that's picked up, that's reflected by the density. That's great. Yeah? And always be very careful. Here we talk about the analytic function. Here we talk about the analytic function. There's nothing random going on. But here we have a realization of this distribution function. Here the randomness is going on. This is the stochastic picture. This is the analytic one. Yeah?
Sorry, how did you generate that picture on the right side?
How did you generate? Yeah, very good question. How did you generate that picture on the right side? There are several algorithms available to do that. I will point out, hopefully, otherwise remind me later. But yeah, I could use conditional copulas to do that. The first component I know is standard uniform, so that I can already generate. But then the second one, I have to generate as a standard uniform, but in a very specific way dependent on the first one. And that dependence is given by the conditional copula. So the conditional copula given the first component. So I have to do the two things at a time. And there you see why dependence modeling is so tricky, because not only do I have to keep track of the margins, I have to keep track of the dependence between the components. So that would be one approach. And that would be a one-to-one algorithm. I start with D standard uniforms, and I map them to one random vector, D dimensions, dependent according to that copula. That would give me one of these points. This is, because it's a one-to-one transformation, I can not only feed it with pseudo-random numbers, I can feed it with quasi-random numbers to get variance reduction and things like that. So that's very interesting for these types of applications. Yeah, but it's not the fastest way to generate from these copulas.
Smoothing on that graph here? Smoothing.
In what sense smoothing?
Density smoothing. I look at it like this, the density plots. You somehow smooth the points and look and get the right picture.
Yeah, I think one can do that, yeah. Yeah, one can also, in that sense, smoothing. What's done in higher dimensions is also binning. You would bin the data first, and yes, yeah. You can also do that. I mean, here you have the level plot essentially. So that's the exact plot. That's the exact plot. But you can also do that empirically. Of course, if you have real data, not generated, then I don't know the exact copula. I can look at the empirical distribution functions. So all of these concepts that exist for multivariate distributions also exist for copulas, obviously. Copulas are multivariate distribution functions.
Is that a contour in R?
That's the level plot function from the lattice. I'll show you more on that. I'll show you more on that. But yeah, you can use the contour function as well. And here also from the contours, you see a higher concentration of points in the lower left corner. But let me just quickly give you one more notion here. So a fast way to generate this sample would be through the so-called Marshall-Olkin copula. Yeah? That does not look at a one-to-one transformation with these analytic conditional copulas, which are sometimes tricky to get, but it looks at a stochastic representation as well. So for these copulas, you can have a very simple stochastic representation. So a little bit how we started in chapter 6, thinking about stochastic representation.
I think this is really important. I mean,
okay.
It's relatively easy to
yes.
sample from
Yes.
from these components.
Yes. So the way you could do that is as follows. So this is a stochastic representation of a random vector from an Archimedean copula generated by psi, where these E1 to ED are standard exponentials, IID, and independent of V. V is the so-called Freity variable, and the Laplace, it's a random variable of a distribution function on the positive real line. And that distribution function, let's say f sub V, the Laplace or Laplace-Stierges transform of which is the generator. Yeah? So somehow the generator is linked to that V, otherwise I would not get standard uniform margins. Yeah? Very easy proof to show that this is actually following the copula C, given in this functional form here, yeah? Given in this functional form. If this is too daunting to you, just take one of these components. Yeah? You can also show that this is indeed standard uniform. And this is now at the corner of course, making this more flexible, more asymmetric, yeah, going away from exchangeability. So Alex has done work on replacing that V by different Vs. They depend on each other in a nested way. That gives you nested Archimedean copulas. Then Alex has also done work on replacing these IID unit exponentials by gamma distributions with different parameters, I believe. So the Liouville copulas then, yeah? So you have various extensions here. Yeah? And it's a good remark to quickly at least write this on the board, because here we are again in the stochastic world. Here you have a stochastic representation, and you would see from here how to generalize that, yeah? What are the options to get more flexible models. But again, these models are more tricky to handle, so we try and learn from the basic building blocks essentially first.
This is described in the book?
Yes, yeah. Yeah. That's all described in the book.
It's very nicely constructed. It's really nice. Nice.
Okay, then I also put up a realization of a three-dimensional sample. That's the max we can visually represent essentially as a full sample. So a three-dimensional sample here would be 3, and you still see this concentration of points in the lower left corner. And if you were to project this sample to each of the sides, yeah, so in the xy plane, in the yz plane, for example, then all of those pairs you see on the right side, yeah, so they all look like this sample here, yeah? And this is the exchangeability essentially that you see. So in higher dimensions, or at least moderate dimensions, what people like is to look at these pairs plot, where you at least see all the bivariate samples, or copula samples in this case. There are possible extensions in higher dimensions, but mostly you would look at pairs only. Good, then some pictures for the Gumbel copula. So again, you don't see a big difference between the Gumbel and the Clayton as a function, as a distribution function. But if we study the sample, then this looks differently. So instead of a concentration of points in the lower left corner, we have a concentration of points in the upper right corner. So the Gumbel copula has this notion of so-called upper tail dependence. We make this precise later. And what this means is that given that my U1 is large, I have a high probability that my U2 is large simultaneously. And these are the types of things we are interested in for risk management. Given that one risk factor change is large, I have a large probability the other one is large too, so those are the events that we might worry about or might be interested in modeling. Yeah? Now, you can say, hey, for that risk factor changes, one component large being the other one being large, this is what we are interested in. The Clayton copula, why did you show me that? Because I never see the high concentration of gains anyways. Yeah? The reason for that is I can simply make this model more useful by flipping around that sample. Yeah? And flipping around the sample, in the bivariate case, rotating it by 180 degrees, is very easy. All I do is I generate the sample from the Clayton copula, and I build 1 minus U1 and 1 minus U2 instead of U1, U2. Now, if U follows the standard uniform distribution, 1 minus U also follows the standard uniform distribution. So the marginal distribution I didn't change. It's still standard uniform. So my new rotated sample has an underlying copula, yeah, as distribution function. Not only has an underlying copula by Scarcity theorem, the margins are already standard uniform, it is distributed according to some copula. Yeah? And that would be called the so-called survival copula. So by looking component-wise at 1 minus the U's instead of the U's, I can bring this concentration of points up here and therefore get a model similar to the Gumbel, but not exactly the same. But if those are the types of shapes, geometric shapes I see in my sample clouds, then I have more than the Gumbel as option. I have the Gumbel, I have the survival Clayton as option. Yeah? So by flipping around samples, you can generate the so-called survival copulas. Very important as well for generating new copulas, if you like. Good, and then the corresponding density, you see a high concentration of points up here, the corresponding level plots. Yeah? And again, there's a whole R script about copulas I quickly look at, go through with you, and there are even more examples available. Cloud plot as before in 3 dimensions, and the corresponding pairs plot. Yeah? So see the pair U1, U2 I see here is the one I would get by projecting that sample in the XY plane. Yeah? Good, now advantages of these copulas, they are, as I mentioned, they are typically explicit because of this explicit construction. All sorts of properties about these copulas, interesting properties, the symmetries and so on, the notion of tail dependence can be characterized or can be given in terms of that one-place function psi or properties of such. So this is very nice in some sense. It's a little bit, just philosophically, if you like, a little bit like the normal variance mixtures, where we just added one factor, one univariate random variable, the square root of W, and we got something new. And here, that univariate random variable would be the V, and we can express most of the properties in terms of V, as we could express several properties of normal variance mixtures in terms of the distribution of the W. There was another question? No? Okay. Good. Then densities are available in many cases. The Clayton, the Gumbel densities are available. Sampling is often easy. Well, that we already discussed. Yeah? So this is typically easy. For example, to get the Clayton sample, that V would simply follow a gamma distribution. Yeah? So it can be done easily. And we are not restricted to radial symmetry. So we are not restricted to symmetry with respect to the secondary diagonal. But we are restricted to exchangeability. So we are restricted to functional symmetry of the copula. And the number of parameters of these models are typically well below the D choose 2 as we had for the Gauss and T copula. Yeah, so typically, our classical examples, Clayton and Gumbel, have 1 parameter. As I mentioned before, there are extensions, so you can have more than 1 parameter, but often you have a small amount of parameters in these models. Yeah? Good. Now, there are 2 notions I quickly want to mention. I already said before when we looked at the equation in Scarcity theorem, F being C and the margins, I said we can keep one fixed and play with the other, so this is that. Can study the so-called Fréchet class, that those are all the distribution functions that have fixed marginal distributions, F1 to Fd, but can have any copula. and that we will essentially, for Frichet-Glass, we come back in Chapter 8. And we can construct meta-C models. Those are all possible distribution functions you get if you fix the copula, but let the marginals vary. Now, there's an example. For example, if you say we study a meta-T model, that just stresses that we use the T copula, but any type of margins. Now, here's an interesting question for you. If I use the T copula and T margins, do I get the multivariate T distribution? Yeah, so are all, so do I get the multivariate T distribution?
Not necessarily.
Okay.
Different,
Yes, very good, very good. So the multivariate T has 1 degree of freedom. It's 1 degree of freedom nu for all of the components. Yeah? If I study a meta-T model with T margins, then my T copula has that degree of freedom parameter from the multivariate distribution, if you like. But my margins are T themselves, but they can have any degree of freedom I choose. So a meta-T with T margins is more flexible than a multivariate T. So they're not equivalent. But of course, if I choose the univariate T's to all have the same degree of freedom as the T copula, then I get the multivariate T distribution. Yeah? So you see, it's a bit of copula engineering now, or like multivariate distribution function engineering now. So we can design, we can use a specific copula and have more flexible margins. We can fix the margins, have a more flexible copula, and so on. Yeah? So also for practical applications, very often you have a good knowledge about your marginal distribution functions, but you do not know much about the dependence. So you can do the modeling based on different copulas on top of your margins, and then study whatever outcome you're interested in, whatever model, and you see how much your results vary in terms of the copula you choose. If the results vary a lot, then you should be worried about correctly specifying the copula. If it doesn't vary too much, then it's probably not so important to specify the copula correctly. So a bit of copula or multivariate distribution function engineering. Now, simulation, we already mentioned that before, essentially. So implicit copulas, I would, of course, go from the multivariate distribution I started with. So that's Chapter 6. I have a lot of distributions available there, elliptical distributions. I can sample them, discuss the stochastic representations, and all I need are the marginal distribution functions to apply my probability transformation to recover the U, the sample from the underlying copula. Yeah, so this is the first part of Scarcity Theorem, if you like, used as an algorithm for sampling. But of course, I need to know how to sample the multivariate F, and more specifically, I should know explicitly the marginal distribution functions in order to make this comparably quick. Yeah? So that can be a problem, but for the multivariate normal, multivariate T, this is of course easy to do. Yeah? So these are the two examples, as I just mentioned. So there's not much more to discuss. Those are the stochastic representations we had in Chapter 6. And here again, you see I start from the location scale transform, from the standard multivariate normal, if you like, essentially. Yeah? So I don't need to, I have a correlation matrix here, but I don't need a mean vector or variances involved here. I would just simply get the same copula. Good. Then sampling meta distribution. So I fix a certain copula, and I want to look at all possible margins. There's not so much I can do explicitly unless I know the margins, but I would need to know how to simulate from the copula, and then, of course, I just apply my marginal quantile transformations to go from the U space to the X space and get my margins. So, for example, I could use the Clayton model, simulate from that with this algorithm, and then I could put on top a Pareto margin and an exponential margin, or an empirical distribution function as well if I have a lot of data, and get a more realistic sample. So the marginal distribution functions I could estimate first if I have enough data for that, and then I could sample from different copulas, use that transformation to get different multivariate distribution functions with the same marginal distributions I want, but different copulas on top, and those are the different samples I could then study whatever model you are interested in. So that's quite nice. Now, the question is, of course, how do you sample in general from a given copula? And there are algorithms available, but very often they are tailored specifically to certain families of copulas to make them quick. Now here you see a sample. It's also available as an R script online from different copulas, a normal copula with correlation parameter 0.7, a Gumbel copula, a Clayton copula, and a T copula. And in the next step, I'll put on top marginal, with the marginal quantile transformation, marginal normal distributions. So let me do that for the 4 samples. And as it turns out, I chose the parameters of these copulas such that all of these samples have correlation 0.7. So you see that, you already see here that specifying the marginal distributions and the correlation coefficient will not uniquely specify a model. We will come back to that soon. So you have very different shapes here, all have the same correlation coefficient, all have the same margins, but you have very different dependencies. Good, now there are, of course, many other properties of copulas we could study. The symmetries are kind of important. Those are the things you first discover if you look at pseudo observations. But yeah, copula densities we also already quickly mentioned for the normal. So you can decompose also your density in this functional form as we already mentioned. And that is quite nicely decomposes or leads to a decomposition of the logarithmic density. And there you have a part that only depends on the marginals, and you have a part that depends on the marginals and the copula, and you can actually do the optimization separately in a 2-step procedure. Let me just very quickly, it's not so important for us, but very quickly mention that this is extremely powerful from a statistical point of view. Essentially, it tells us that we can first estimate our margins, parametrically, non-parametrically, very often parametrically, but then actually non-parametrically estimate the corresponding copula parameter, so you can do the 2 things separately. And one classical example I always give is that if you have a 100-dimensional model, all your margins are normal, you have 2 parameters, you have a Clayton copula, let's say, with 1 parameter, then I have overall 201 parameters to estimate. If I don't have this notion of copulas available, then I would have to solve a 201-dimensional optimization problem, whereas if I have this notion of copulas available, I can first estimate my 100-dimensional marginals. I can do that independently of each other. I can do that in parallel if fitting the marginal involves Armagard type of modeling, Monte Carlo, and so on. I can do that all in parallel, and then I have a 1-dimensional optimization problem for getting the copula parameter. And that's, from a numerical point of view, extremely helpful. You can fit high-dimensional models suddenly because of this decomposition. But that's mainly the first part of Scarcity theorem, decomposing my F into C and the margins. That's what's contained in here. But it's extremely helpful, and also very often, if I have 100 dimensions and I have parametric margins, I cannot make sure I specified all my margins correctly. So I would actually base that copula parameter estimation based on non-parametrically estimated margins. And since I can do that based on my data immediately, ranking the data, I can do it doesn't depend on the marginal parametric models anymore. So I can estimate all of the parameters in parallel, actually. So there's a lot behind there we cannot discuss. There's a larger R script on estimation and also goodness of fit online as well. But just you see all of that essentially from here, and the decomposition in general. Good. Now let me just quickly check. Yeah, let me just. So let me just quickly skip the examples. I think we discussed most of them in detail already on the pictures. There are many more pictures in the R script. Examples of copulas. There are more general examples also that are in between, something like the Fréchet-Höfting bounds and something absolutely continuous where I have a density like the Clayton and the Gumbel copula. There are many animals in the zoo. Play around with that R script. It's a really nice one. But let me move on to summarizing to summarizing the dependence in a copula by univariate quantity. Because if your boss asks you about the dependence between the risk factor changes and you tell him it's an outer power Clayton copula with parameter 1 and 3, expect more questions. Yeah? So we want to, the idea here in 7.2 is to summarize dependence in terms of a univariate quantity. Yeah? And we want to think about reasonable quantities to do that. Now, perfect dependence, we already discussed perfectly. I would say we already discussed it in detail at least. Yeah? So the Fréchet-Höfting bounds, I don't have to stress that anymore. But the linear correlation, of course, comes into mind first when we think about measuring dependence by univariate quantity by a number. Yeah? Something in between -1 and 1, where we have an interpretation of the extreme cases -1 and 1 through linearity, yeah, through very strong positive dependence. And so the linear correlation we could use. There's one formula which you may have not seen before. It's called Höfting's formula, which allows you to rewrite the covariance in terms of this complicated formula. Yeah? But we will come back to that and see why this is helpful. Now, at this point, you already have in your pockets Clark's theorem, and every time you see a multivariate f, you replace it by C of f1 to fd. So you already see here C of f1 to fd minus essentially C of f1, well, C of f1 and f2, here C of f1 and f2 under independence, because it's the product here. So in some sense, by measuring a certain distance, if you like, yeah, between your multivariate distribution and the multivariate distribution under independence, you can express the covariance. And that's going to be very helpful for us for studying the linear correlation.
Can you go backwards?
Yeah.
I always find it a very interesting example. It looks totally easy. So, well, surely this must be a trivial proof. Try it. I'm sure you don't find it.
And look up the proof in the book.
The proof in the book, it's perhaps 5 lines,
yeah.
6 lines. But then you ask yourself, how did Vasily Höfting ever come to that idea?
Yes.
And it's so trivial, but trivial looking at it.
It doesn't give anything away if I tell you at the start of the proof, you start with 2 times the covariance. And you have no idea why you do that. Yeah, it's very nice. Look at it. It's wonderful.
My students,
yeah.
The brilliance of some mathematicians. How did they find this?
Yeah, yeah.
Nice example. Go to the book. Well, first try yourself. Multiply by 2. Think about it. And after a couple of weeks of trying, look how Höfting did it in 5 lines.
Okay.
Even if you know the answer.
So yeah, we come back to that formula. Here is just a summary of properties of the correlation coefficient. Paul already mentioned much earlier, of course, that the correlation coefficient is 1 if and only if you have linear dependence, almost surely. Yeah? Almost surely one random variable is a linear function in the other one. Yeah? So this is, but this discards, of course, other strong functional dependencies we might be interested in. Yeah? If I tell you that x2 is x1 squared, essentially, yeah, that's a very strong dependence. Both of the random variables move in the same direction. So by the invariance principle, we already know underlying we have the strongest possible positive dependence, the upper Fréchet-Höfting bound. Yet, because we have a quadratic function and not perfectly linear, we cannot get correlation 1, which is very unintuitive because it's like a very strong dependence between the 2 components. Huh? So linear correlation doesn't capture that. It captures linearity, but not much beyond. Then x1, x2 are independent. If x1 and x2 are independent, then the correlation coefficient is 0. The converse is not true in general. We looked at that, for example, 2 uncorrelated t's we looked at, but because of the square root of w, they are not independent. Yeah? So uncorrelatedness does not imply independence. And rho is invariant under strictly increasing linear transformations. That's an easy exercise to do, but not invariant under strictly increasing functions in general. That we essentially already discussed by looking at a quadratic function. if I apply a non-linear transformation, you see my correlation coefficient underlying changes from 1 to something smaller than 1. So you see the correlation coefficient is not invariant under strictly increasing transformations of my components in general, although the underlying copula by the invariance principle doesn't change. So correlation doesn't only measure the dependence, or doesn't only summarize the dependence contained in the copula, because if it did and the copula doesn't change, it wouldn't change. And this also, of course, is very obvious from the definition. The correlation coefficient not only contains something about the dependence contained in the covariance, you divide by the standard deviations. Yeah? So it also depends on the marginal distribution functions. Very simple example. If you have a very heavy-tailed Pareto distribution with no finite second moment, you don't have a correlation coefficient. It simply doesn't exist. Yeah? So also depends on the marginal. So these are the kind of drawbacks we have. Now, there are a couple of correlation fallacies, so misbeliefs when working with the correlation coefficient. And some of them we already touched earlier. So the first fallacy is that if you give me F1 and F2, specific marginal distribution functions, and a specific correlation coefficient, let's say 0.5, then that uniquely determines my joint model F. Now, if you see F and you see F1 and F2, immediately that C pops up in the equation of Scarcity Theorem, so you know, C uniquely combines my marginals to the joint distribution function, but C is a whole function. Now you replace the information contained in the whole function by a single number. You should doubt that you can do that. If you could do that, then we would not be studying copulas. We would study that one number.
Well, people in finance often think they can do it.
Yeah.
But still, that's one of the big errors in finance. Constantly. Even today.
Yeah, so a lot of papers, you can find the word correlation, but it actually often means dependence. So be careful, correlation, linear correlation versus dependence. Now we looked at this before essentially, right? I showed you the 4 pictures, 4 different samples of copulas, all have the same standard normal margins, all had correlation coefficient 0.7, yeah, but they are very different models. So this is essentially just empirically a convincing example. But of course, you can also, you say, I'm a mathematician, I want to have like a more convincing explicit example. This is a very nice one. So take a look at 2 risks, one being a standard normal and the other one being a standard normal multiplied with a Rademacher random variable. That's just one that puts mass 1/2 at -1 and mass 1/2 at +1. So you switch the sign randomly. That's the ideal. Then both, of course, it's like a stress factor, yes. Yes, yes. So if you flip around a standard normal, if you multiply it with -1, yeah, you still get the standard normal. So both are marginally standard normal. And what's the correlation coefficient? So since they're both standard normal, the variances are 1. So the correlation coefficient is simply the expectation of the product of the 2. Now I plug in my stochastic representation. I use that V is independent of Z, so I get the expectation of V times the expectation of, I don't even care anymore, because the expectation of V of a random variable that's with probability 1/2 -1 and with probability 1/2 +1, the expectation midpoint is 0. So you see that in this general setup, you get the correlation coefficient to be 0. But another model to get correlation coefficient 0 and the margins being standard normal would, of course, be to take 2 independent normals. 2 independent normals also marginally are standard normal, but they are independent, whereas here are these independent? No. They are dependent in a very specific way. So with probability 1/2, they are dependent according to the upper Frescher-Höfting bound. They both move in the same direction with probability 1. With probability 1/2, this is -1, so they actually move in different directions. So what do I have? I have a convex combination between the lower Frescher-Höfting bound and the upper Frescher-Höfting bound. The 2 largest, most extreme possible dependencies I can have. Between W and M. That's very, very different than the independent case. So you can also consider, this is what's contained here, two independent standard normals, and this is essentially what I explained. You can write down the copula of this if you like. It's this convex combination. And of course, you can also put different mass on the lower than the upper Frescher-Höfting bound. That you can do as well. So you can explicitly say what the copula is. Very, very nice example. Not the,
One slide?
not the, yes.
Just, this is going back to Frank's point. You see the first line, that's why it's called the fallacy. This is true for bivariate elliptical distributions. Now you were a bit surprised when I said this is used still every day in finance. It is, because so often models in finance implicitly assume this ellipticality. You see, that's the point why we wrote the paper with Alex and Daniel Stroman in the late 90s, where these early fallacies was based because people implicitly in their models assume this elliptical world, geometric Brownian motion, whatever. And then, of course, they always say, well, it's true, it must be true. Yeah, in that world it's true. You don't have the fallacy, you don't have the error. But the reality out there is non-elliptical. It's absolutely non-elliptical in risk management situations where it matters. You see, that's the answer to your question.
Yeah, I'm still amazed that after so long
No, that's
people...
it. Believe me. Okay, sorry.
Okay, the second fallacy is then, well, if the margins and the correlation coefficient do not uniquely specify my model, can I at least, with given marginal distribution functions, construct in some way a model that gives me all possible correlations? Yeah? And exactly the paper Paul mentioned, it goes back to the mid-90s essentially, where I think 2 insurance companies asked roughly at the same time about how do I construct a model with log normal margins and correlation coefficient 0.5. Yeah? So the fallacy is to believe I can attain with a certain model construction all possible correlations if I specify just the marginal distribution functions. This is true for in the nice world of elliptical distributions, of course, because there my correlation matrix of X, again, if it exists, is equal to rho, so I can put in whatever I want, essentially, yeah? Whatever I would like to have. Yeah, but if F1, F2 are not linearly related, then I will not reach the correlation coefficient 1. Again, we already mentioned that before. So there's already a gap between 1 and, well, I don't know yet. 1 I don't reach, right? This is the point. Now Höfting's formula comes into play that tells me what's kind of the range of possible correlations I can get. Because with Höfting's formula, I know my covariance I can write like that. Now I plugged in Scarcity Theorem here, yeah, for my joint F. And now I see something very interesting. Although the covariance, the definition, depends somehow on the dependence, but also on the marginal information, from this formula I immediately see that the covariance is increasing pointwise in the copula. And this is something you would maybe have not expected from looking at just the definition of the covariance. So if I increase pointwise my C, then I have a larger value in here. I integrate more, I get more. Yeah, so the largest possible covariance I get by the largest possible copula, which is, what's the largest possible copula? The fully dependent one, the upper Frescher-Höfting bound, exactly. Now you see the beauty, the Frescher-Höfting bounds coming into play. Now what's the smallest possible covariance I get? By the smallest possible copula, that's the lower Frescher-Höfting bound. Yeah, so immediately the Frescher-Höfting bounds give me this possible range of largest correlation. I can also reach everything in between by the convex combination we already looked at earlier, the convex combination between the two. Yeah, but the point is, there is such an interval, which maybe is not -1 to 1, yeah? And I get the extremes with the extreme dependencies, yeah? the Frescher-Höfting bounds. Now here's a plot, again, it's online, you can reproduce that if you like, for that very classical example of the log normal margins. And you see here, if my first log normal margin is log normal 0.1, and my second one is log normal 0.16, for example, so I have 1 in sigma 1 and 4 in sigma 2, then you see the difference between this and 0 and here for the upper bound, the difference between 0 and this function. Yeah? So this is the corridor of possible correlations I get. It's almost indistinguishable from 0. Of course, you can numerically evaluate this, and these are the possible correlations you get. Yeah, so if numerically you would get a correlation of, let's say this, the largest possible value, you would say, this is so close to 0, I have independence. No, you have the upper Frechet-Höfting bound here in this case. Yeah? Perfect dependence. Largest, maximally away from independence. Yeah? So here you see how dangerous it can be to think about dependence in terms of the correlation coefficient.
Exactly this example in mid-90s, why we wrote the paper. Because we saw so many confusion around exactly these constructions. And we wrote the paper with Alex. That exploded the interest in copula.
Okay, yes? Yeah, sure.
Here you have 1 in 16.
Yeah.
You say, okay, near advance, so huge. So how, if they're, let's say, if I take 1001 and 1016, and at least for the upper bound, it doesn't change.
Yeah, you see.
It does not depend on, but how, it only, you can say the upper bound, if you have different sigmas, then they're almost uncoded.
Yes, that's why I encourage you to look at pictures. You see a lot here. For example, if the two sigmas are the same, I actually do reach the upper bound 1. Yeah? But if they are the same, I still do not necessarily reach. So there it depends on the value. If they're both small, I do reach. If they're both large, I don't. Why does this hold for the lower bound, not the upper? You see, there are interesting questions around here. Look at plots. Yeah?
By the way, you can write down the analytic formula.
Yes. All you need is the Laplace transform of the univariate standard normal. Yeah, yeah. But let me maybe just this third fallacy to close this part. So the third fallacy is that my maximal correlation, yeah, so I get for the upper Frechet-Höfting bound, my maximal correlation will also give me the maximal value at risk. Now this goes back to chapter 2. Yeah? But under the maximal correlation, so the upper Frechet-Höfting bound, the strongest possible positive dependence, one can show that value at risk is additive. Yeah, so I have equality here. In particular, I'm sub-additive. Now, go back to chapter 2. In the very end, we discussed various setups under which we had super-additivity. Yeah, heavy tails, for example, yeah, very skewed marginal distributions, and so on. And you see that in all of these super additivity examples, we got something larger than we would have gotten, something larger, value at risk of the sum of the risks, larger than the sum of the value at risk, something larger than under the upper Frechet-Höfting bound. Yeah? So in all of these cases, they were actually different from the upper Frechet-Höfting bound. And you can go back and check. Yeah? Okay, thank you very much.
Just
yeah.
Okay. I think that will slightly fast the last statement, I repeat that statement, that the upper Frechet bound you achieve in the comoratonic, that's the comoratonic case. So that's, as Mario said, that's very important. So if you look at these curves, the upper curve, the worst case you can achieve is the comoratonic model. Then Mario said, in the comoratonic case, so if you have comoratonic risks, perfect dependent risks, then the quantile measured value at risk is additive. You can prove that. We didn't do that, it's in the book also. That's not so difficult. That's an exercise. And so I just stress it again, because that's his important second bullet point. In the background, you use a fact for, as Mario said, for comoratonic risk, perfectly dependent risk. The value at risk is an additive measure. The value at risk of the sum is the sum of the vars. And as I said, as soon as I give you any example where it's super additive, then you get an example of that fallacy.
Cannot
and
be.
Again, of course, in the elliptical case, it doesn't happen. Okay, break.
Okay, yeah. Thanks. See you after the break. Let's continue. So, now that we talked about the deficiency of the correlation coefficient for measuring dependence, of course, I should present to you some alternatives, measures of dependence or measures of association, they're also called. And there are two possible things we can consider. Overall dependence, like summarizing dependence if you like, and for that we have so-called rank correlation measures, or just focusing on the lower left or the upper right region of the joint distribution with tail dependence coefficients. So I want to just very quickly look at rank correlation coefficients because we are mostly interested in the bivariate tails, so I want to spend a bit more time on the tail dependence coefficients. But it's good to have heard about rank correlation before. So rank correlation coefficients are, first of all, always defined. Unlike the correlation coefficient, which only exists if your margins have finite second moments. And then they are also invariant under strictly increasing, not only linear, but in general strictly increasing transformations. And with these two requirements, you see strictly increasing transformations immediately. The invariance principle pops up, so we are in the copula world, so these are the types of measures we are interested in. Now, we will very quickly talk about two possible such measures. They're called Kendall's tau and Spearman's rho, and how they're constructed. But yeah, so they are especially used for estimation purposes, comparing different samples. We use them a lot in our R scripts as well. Yeah, so I want to quickly explain the concept to you. So the idea is to measure monotonicity between the sample points. So let's say I have two realizations of the same bivariate random vector, x1, x2, and let's say x1 prime, x2 prime. IID realizations. I can draw a line between these 2 points and measure whether that line has positive slope or negative slope. Yeah? And positive slope means increasingness, negative slope means decreasingness, essentially. And Kendall's tau uses that idea to capture monotonicity in the data, and it essentially computes the probability of that slope between two IID realizations of that distribution being positive minus the probability that the slope is negative. So it measures concordance, so a positive slope, a positive relationship between the two random variables, increasing function, versus a decreasing function, probability of discordance, probability of having a decreasing function. And so as such, probability of concordance minus probability of discordance, it's immediately clear it's a measure between -1 and 1, which is nice, right? So -1 and 1, we already know from the linear correlation coefficient, so it's normalized. And also 1 and -1 correspond to the most extreme cases of lower Fresher-Höfting bound and upper Fresher-Höfting bound for this measure of rank correlation. And because if all of my points lie on an increasing function, so x2 is an increasing function in x1, then all of these lines I draw between the 2 points have positive slope, so the probability of concordance is 1, probability of discordance is 0, so I get +1. And the same works for the lower Fresher-Höfting bound for -1.
This is also one of the reasons why I come back to these implicit errors that very often in credit risk, people stress test credit portfolios by stressing the correlations, linear correlations. Let's say, let's move up the linear correlations even to 1. As Marius already explained, very often you cannot move it up to 1. Of course, you can always do it on the computer, but then you get nonsense. Whereas if you do that kind of stressing based on rank correlations, like Kendall tau, you can do it. So in that sense, using rank correlations, for me at least, is a much more natural measure of dependence as a number in credit risk.
Yeah, and of course, if I give you such a measure, you see it's even defined in terms of the axis, so in my X space, essentially, statistically, then why does it only depend on the underlying copula? Why is it really a measure that only captures the dependence and not also has to do with the margins, as the correlation coefficient. And this follows from this representation. Essentially, Kendall's tau can be written as in the standardized form as the expectation of the copula itself, and you plug in U1 and U2, which jointly follow the copula. And so this is a random variable. You take its expectation, you properly normalize it, you get Kendall's tau. And as such, you see there are no margins involved anymore, so you see that it's really a quantity that only depends on the underlying copula. It only measures the dependence and cannot be distorted by the margins. Then there is Spearman's rho. Spearman's rho is typically a bit easier to grasp. It's simply the correlation coefficient, now here it appears again, but computed not based on x1, x2, but the transformed, the probability transformed random variables. So essentially your U1 and U2. Yeah? And because I compute correlation based on U1, U2, U1, U2 are marginally standard uniform, I have all the moments existing, so this is a quantity that always exists. Yeah? So the correlation coefficient is in that sense not that bad, you just have to apply it to the right random variables. Yeah? And as such, it's also immediately clear, but also clear from this formula here, that it only depends on the underlying copula, because once I do the probability transformation, I am essentially with U1 and U2 here, no margins involved anymore. Yeah? So as I...
This is regardless of the margins, right?
This is regardless of the margins. Kendall's tau we very often compute from the original data, but you can first compute the transformed ranks, if you like, and compute Kendall's tau based on that. It will not change, because going from the X space to the U space, the underlying copula doesn't change, therefore my Kendall's tau doesn't change.
If you use something that, for example, where the rho doesn't exist for the marginal, you still can compute the...
Yes, so in the case where I have infinite variance, infinite second moment for my margins, the correlation coefficient doesn't exist, yet still I can do this, and therefore Spearman's rho and Kendall's tau exist. Now, they only depend on the underlying copula, not the margins. So the existence is always clear. Now, to be fair, we would have to go back to the fallacies and discuss which of these fallacies we can now solve with rank correlation, which we couldn't with linear correlation. Now, the first fallacy says the unique characterization of F in terms of the margins and the correlation coefficient, that we can actually not solve by using rank correlations, which is clear. We know the margins plus the copula give us the whole distribution function. Still, we replace it by a single quantity, rank correlation in this case. We cannot expect to have a uniquely defined multivariate model. And we do that very often by comparing samples. We have the same Kendall's tau, Clayton and Gumbel copula, same margins, but you have different sample clouds. Then also, can I, if I replace correlation by rank correlation, can I always construct a model that has rank correlation in between -1 and 1? That's coming back to exactly what Paul said. And this is always possible. Simply take a convex combination between the upper Fréchet bound and the lower Fréchet bound. They have Kendall's tau, Spearman's rho, for example, 1 and -1, and with that convex combination, you can always reach all possible values. Again, I have to cut down a little bit here, but it's a small exercise to go from that model to these results, so that can all be done. Fallacy 3 is that the misbelief that the largest possible dependence, the upper Fréchet-Höfting bound, gives me the maximal value at risk. That can also not be maximal correlation gives me the maximal value at risk of the sum. That can also not be solved by looking at rank correlations, because rank correlations being 1, let's say, Kendall's tau being 1, Spearman's rho being 1, still only so to say, relate to the copula being the upper Fréchet-Höfting bound, but in our sub-additivity examples, we saw that we got something super additive instead of additive, which it would be in case of the upper Fréchet-Höfting bound. So this we essentially already discussed also before the break. But nonetheless, rank correlation measures are very useful to generate, let's say a Gumbel copula with kind of a mid-range dependence. I would choose the parameters such that Kendall's tau is 0.5. I can do the same for Clayton. If I give you Kendall's tau 0.5, you roughly know what the dependence is, whereas if I tell you the dependence for the Clayton is 3 and the parameter 3, and for the Gumbel it's 5, you do not know how to compare these models. So as such, it's very helpful to have these summary measures. that's statistically there's a difference, and for some models you have Kendall's tau available, but not Spearman's rho, and so on. So, but I can give you more details. It's more on the statistical side. Huh?
Also in the original paper that we wrote with Alex and Straumann, we refer to work like Scarcity. We have a whole set of axioms there. What are possible right correlation constants? So that
there are many more. There are many more. There's Blomqvist beta as well. There are many more of these measures. And when it comes to parameter estimation, it makes a bit of a difference.
The problem is if they have more than one option, people start firstly, people mix it up, one with the other, or people that know a bit better use the one that's more convenient for their purpose.
Well, personally, I mostly work with Kendall's tau. It has statistically nice properties. It's available in explicit form for most copulas. Kendall's tau I would prefer in general, if you like. Good. Now this is summarizing general dependence. Huh? So now we want to look at the tails. And we already looked at the sample clouds before. The Clayton copula had concentration of points in the lower left corner, the Gumbel copula concentration of points in the upper right corner, and we want to make this a bit more explicit now. And the mathematical concept to use is the notion of tail dependence. And it's defined as follows. So you have two random variables, x1 and x2, and you call them lower tail dependent if the probability that the second one is small, if there's a positive probability that the second one is small given that the first one is small. Order doesn't play a role here, can be easily shown, but yeah. So the probability that one random variable is small given the other one is small. If that in the limit for small quantiles, it gives you something positive. We call the two random variables lower tail dependent, otherwise lower tail independent. And the same concept for the upper tail dependence coefficient. So there you look at both random variables being large. So probability that the second variable is large given that the first variable is large. Now, being large can mean something completely different for the two random variables because still the marginal distributions are involved. Yeah? So 100 might not be as large for Pareto as it seems for an exponential distribution. Yeah? So so we have to make sure we measure large for the two random variables in the same way. And this, of course, is captured through the quantile functions here. So you look at the same quantile, but you look at the same probability level, but you still have the different quantile functions, and then they determine what it means for each of these random variables being small or large. And of course, again, as before, you see the marginal distribution functions involved. Why is this a notion that only depends on the underlying copula? Well, that is a very simple calculation. You look at the conditional probability. This is an event with positive probability, so this is an ordinary conditional probability. It's just a joint probability divided by the margin. Then you use the standard trick you used all the time, proof of Scarcity theorem in many ways. You bring the quantile functions to the other side. You have essentially your u's there, probability that u1 is less than little u, probability that u2 is less than or equal to little u2, and this is simply u itself. So you see that the lower tail dependence coefficient is simply the limit if you go towards the lower left corner on the diagonal of the copula divided by u. Yeah? So you go towards the lower left corner, and you see with this form that, of course, the notion of lower tail dependence only depends on the underlying copula, not the marginal distributions anymore. Yes?
Can there be weird cases where the limit doesn't exist?
Yes, there can be one. There's a paper by Korczak and Albrecher. I can construct one for you later if you like. It's based on diagonal copulas. But yes, I can assure you for all copulas that have names, these limits exist. Yeah, and they are very often explicit, so it's a very nice concept. But you have to construct a little bit a counterexample. Yeah? It's not an intuitive one, but yeah. Now, of course, as I go towards the lower left corner, this goes to 0, and by groundedness, this goes towards 0 as well. So I have 0 by 0 divided by 0 in the limit. So one thing you very often use when computing those is L'Hopital's rule. And you can also view this as a composition, and then you can use the chain rule here to come up with a slightly more complicated formula in terms of any continuous distribution function f. The reason why this is there is that this formula is used to derive tail dependence coefficients of the Gauss, the normal copula, and the T copula. There it's very helpful. These implicit copulas that come from the multivariate elliptical distributions, they are essentially to compute these limits, or very often quantities involving the copula. You play it back to the multivariate distribution where you have a lot of properties, and there you use these properties to derive these results. Yeah, so that's a result we will use.
Just to go back, because pedagogically, just for the student, this last bullet point, if you want to go through that on your own with the book, believe me, it's a bit more work. So it's just accept 25 is a result. And 25 shows you nicely that if you can calculate the conditional density, it exists, then you can calculate nicely what you said, the tail dependence copulas. But a couple of lines in between, believe me, it will take you a bit more time to work through that. It's doable. It's not difficult, but it's just pedagogically a bit aware.
And also pedagogically, it's a very nice example where you really see for elliptical implicit copulas, you kind of always play it back to the multivariate distribution because you have all the properties there. Now for explicit copulas, or Archimedean copulas we discussed, you can have explicit formulas in terms of the underlying generator psi, and you can, it's very easy to derive in 2 lines. That is an easy one, that's a good exercise. Yeah, and the upper tail dependence coefficient can be handled in exactly the same way. This is the corresponding formula for the upper tail dependence coefficient in terms of the underlying copula. Yeah, and you can also use L'Hopital's rule to compute that and so on. Now, there was a good question during the break concerning, you flipped around the copula to put the mass from the lower left to the upper right corner to get the survival copula. What happens if I do that for the Gauss or the T copula? Yeah, so I have the same mass in the lower left corner than the upper right. If I flip it around, I see the same picture. That's the radial symmetry. Now, what happens to the tail dependence coefficients? The good answer is I only have to compute one of them. The lower is typically slightly easier to handle. Yeah, because of radial symmetry, I know the limit in the lower left corner must be the same as in the upper right corner because I have the same probabilistic structure in the corners. Yeah? So there I have the same kind of tail dependencies. Good. For the Clayton, you can then indeed show what we already kind of saw in the sample cloud. So you have lower tail dependence, but no upper tail dependence. For the Gumbel, you have upper tail dependence, but no lower tail dependence. So there are these examples. You can also have Archimedean copulas that have upper and lower tail dependence, and so on. There are many examples, and those are typically easily derived with these formulas.
Can I do, for example, for the Clayton,
yes.
1 minus, in the 2 variable case, 1 minus x1, 1 minus x2, and then I shift the...
Well, for the Clayton, of course, if you look at the survival Clayton, then your 2 tail dependence parameter changes. Now, if I look at the survival Clayton, then, of course, this will be my upper tail dependence coefficient, then this will be my lower one. So the mass, and you also see that from the density. From the density, it's very easy to see. You have the density evaluated at 1 minus the arguments. Yeah? So you're flipping around the sample cloud is stochastically the same as analytically rotating the density. By the way, we have that newly in the copula package, so you can have rotated copulas as well, also by less or more than 180 degrees. Yeah? So you can construct new models. You don't immediately throw away your Clayton if you want to have concentration of points in the upper right corner. So, yeah. But now let's use that formula 25 and think about the tail dependence coefficient of the normal and the T copula. And so for the normal, we have the result that the conditional distribution is, again, univariate normal. So I have an explicit form of the conditional distribution, can be easily shown with the densities, very good exercise to do. And then I plug that into the formula 25, and I see that in the limit, I do get 0 unless my correlation coefficient is 1 and all of my variables lie on a line with slope 1. And so essentially, I have no tail dependence for a bivariate normal copula. And of course, one can mention a whole course here. This result goes back to Shibuya in 1960, and not knowing that the Gauss copula doesn't have no tail dependence was one of the technical reasons, if you like, for the recent financial crisis, essentially. But yeah, that would go too far now. Now for the T, you can use exactly the same approach, and you can show that the tail dependence coefficient is given in this form. It's increasing in increasing rho and decreasing nu, so the more heavy-tailed, the smaller my degree of freedom, the more heavy-tailed I am, the larger my tail dependence, and also the more concentrated my points, the larger my correlation, the larger the tail dependence. To get this result, this is not so easy. It's not so easy. You see, the univariate T, it changes its degrees of freedom. It's also a very good exercise, but it's not so easy to get. Now here you see a couple of samples. You see a bivariate normal with correlation 0.5, and you see a normal copula with T margins. So I just make the margins more heavy-tailed. And you see I reach out further in the tails, essentially, but only along the axis. So because the lower left corner, the upper right corner, the concentration of points there, at least in the limit, would be determined by the underlying tail dependence coefficient, tail dependence coefficients of the underlying copulas. And the underlying copula I didn't change. It's still the normal copula. So I don't see a high concentration of points in the lower left and upper right corner. Now, if I start with, if I look at a multivariate T model, so there I replace essentially, in this plot, I replace the Gauss model, the normal copula, by a T copula. Then, of course, the T copula has lower and upper tail dependence. So you see that marginally, I reach out as far as before. Of course, I have the same margins, but then also jointly, I reach out further in the bivariate tails. So that's a very good exercise. You replace the copula by something that has tail dependence or something that has more tail dependence. You keep the margins, and suddenly you reach further out in the bivariate tails, and we have discussed this many times by now with the BMW Siemens data. This now looks as our BMW Siemens data, so you reach out further in the tail. Good, so this is it for 7, and Paul will...
Quick question.
Yes?
Getting the Spearman rho and the Kendall tau numerically, that's really easy on a experimental sample.
Yes, of course, you can estimate Kendall's tau, Spearman's rho.
Really easy.
Yeah.
However, to compute to infer from a data sample the tail dependence, can you give us a recipe that works? I mean, numerically, it's not that easy to
Okay, there are.
numerically.
Okay, there are a couple of estimators available, but they don't work well. And people that invent them even say they don't work too well. So it's a very interesting point from a pedagogical point of view. So if you are a statistician, you say, I fix the quantile, and then if my sample size is large enough, I am able to observe that concentration of points. So I fix the quantile and I let n go to infinity. That's something the statistician would do, and he would say that he can estimate tail dependence. The probabilist says, no, I have a finite amount of data, n is fixed, and that limit is a limit for the quantile to go to 1 or 0. And therefore, at some point, I don't have any observations in the corners. So it depends very much whether you are a probabilist or statistician, whether you can do it. I tried it a couple of times with different estimators. They overall, it's not easy to get this theoretical quantity from data. That's the short answer. I can tell you the estimators.
You would probably need limit results for n to infinity and q to 1 or 0, and it probably depends. The properties they estimated probably depend on the rate of convergence.
Yes, on the rate of convergence, quantile versus sample size, and
The
practice, you have a finite sample that you have
Yes.
observed.
Yeah.
And getting a limit is numerically always a difficult thing.
It's not easy to estimate tail depends. What you normally do is you fit a copula model, a parametric model, and you take the model implied parametric tail dependence coefficient.
You can, yeah, more questions. Marius?
Just one comment. People who, we talked about statistician, probabilist, and people who want to defend Gaussian copula, and we need those people. They say, well, you cannot take the limit because in practice it doesn't matter, so tail dependency is not an issue, it's just a theoretical aspect.
Okay.
Well, maybe as a comment, in practice, I think if you ask someone who has lots of experience, you underwrite a claim to them, and you ask them a question, what's the correlation between the variables? The guy has absolutely no clue. You actually don't have something which is not intuitive. However, tail dependence, something very intuitive. You can really ask the question, if I have a claim that's larger than 10 million, what is the probability that you have in this other line of business a claim larger than 50 million? This is something that people can answer. They have a feeling for that. They can't give it to you to the last decimal, but they have a feeling for that. That's a very intuitive thing. But that's why the tail dependence is a really useful thing in practice.
You have to build your models according to these expert opinions, probably.
Sure.
And the other thing
If
is,
you don't have data, you don't have a choice.
then the other thing is probably, of course, it's difficult to estimate, but you can simply say, I use it as a model risk testing device. You take a model, you maybe have an answer of the Gaussian copula world, you test it in the T-copula world, you have a little bit of tail dependence. If the answers you're getting are substantially different, then you should probably throw the Gaussian copula analysis back in. If they don't vary too much, you can proceed.
Well, I mean, I can give you, I can join there. I'm not sure I'm going to talk about this, but never mind. It's, first of all, let's say now for our friends and regulators, of course, I mean, for instance, when the notion of tail dependence was introduced, of course, tail dependence is very much a concept really related mathematically, it's just the edge of a very important mathematical field, that's multivariate extreme value theory. Because you ask an extreme value question multivariately, in this case, two variates. And for instance, this tail dependence, what we call tail dependence, is much more importantly called spillover probability. How does a risk in one component spill over to a risk in another component? And of course, this has been used tremendously, let's say. Again, I come back to the Dutch dike building case. So it's very much used in that concept, and people think with finite, not really the infinite limit. Secondly, I still remember very well numerous tables worked out by the European regulators on these tail dependence coefficients. So there are ways at least to think a little bit what the numbers mean. And thirdly, a little anecdote. I still remember when I gave a talk, the first talk on our paper with Alex and Straumann, I think it was I think January or February 1999 at Columbia University. And I showed you the example that Mario showed, where you have the Gauss copula and the T copula on exponential margins. And you clearly see, it was already also in Rudiger's introduction, you see that the T copula on the exponential margin produced extreme events, whereas the Gauss copula did not produce extreme events. And you can count them. I can empirically count them. I'll say, well, if you have data, well, you can just empirically count them. And there are tables in the book also where we do this empirical counting on a finite range, not when u goes to 1 or to 0 or infinity, whatever. And so you can do that. And I still remember when I showed this picture at Columbia, I said, careful, because this really shows that the Gaussian dependence, the Gaussian copula on any margins will never be able to produce sufficiently many extremes. And now you can measure that with this number, you can measure that in any way you like. That's a fact. And during the break of that talk, David Lee came to me. I didn't know David Lee at that point, but David Lee, of course, is the person who very much was behind the construction of the Gaussian copula model for CDO pricing. Came back from, I think it was in those days still JP Morgan. And he came to me and he said, oh, interesting, this graph. And I said, that exactly the graph you saw basically, these two with Gauss and T on exponential margins. We had gamma tree margins, but you don't see the difference. He said, it's interesting, we were using this technology for pricing CDOs. I said, well, of course, I didn't have a clue what CDOs were. This was 1999. I said, whatever you're doing, but careful, and now I come back to the comments here, careful. If this has to do with a risk of joint extreme events, don't use the Gauss copula. It's not going to work there.
But he still did.
Of course I did. No. Wow.
So you could have prevented them from doing all that.
The paper was there. The talk was there. The discussions was there. I mean, of course, I didn't know the products. There will be many more examples. There are some nice examples later on the CDOs where we compare these dependence. With hindsight, we should have shouted much more louder. But I think these examples were actually there. We discussed that.
But they have a nicer story.
I'm sure they have.
I mean, one has to be a little bit careful.
No, sorry, we have to continue. No. Otherwise, I won't get anywhere. So we continue. No, we have to continue now.
Everything on
Yeah.
dependence. If you
Yeah.
have the normal Gaussian copula model for CDO pricing, you can get also a lot by simply adjusting.
Yeah. We'll come back to that later in credit, I think. So let me also slow down a little bit at another level now, because I want to slow down at the level of, before I go to the aggregate, because I have to make a selection now. I want to just briefly put on the blackboard two results, which I think may have gone a bit astray before. But let's say the first result, and again link it to the story. And sorry, I think I want to give these stories because it shows a bit historically the kind of discussions you may still run in today. There's a big discussion now on expected shortfall versus value at risk. On the Basel III, the new discussion, the amendment to the trading book rules, we have actually that discussion going on. Now, again, if X has a normal mu sigma square random variable, okay, you can now look at the limit, and of course we had that result on the blackboard, and this is, and I just give you the page again, page 40, we saw that the limit for alpha going to 1, i.e. you really go far in the quantile tail of expected shortfall of alpha over the value at risk of alpha is 1. Now I mentioned this result, which is a fairly straightforward analytic result. It's basically you compute expected shortfall in value at risk for both. Analytically you can do it in this model, and you use L'Hopital's rule. The second result, well, let me first say this result. And I just want to tell these stories because they may help you in discussing similar events in your environment. When we discussed early introductions of expected shortfall, and again, we're now talking mid-90s already. My colleague Delban, ourselves, we said, well, there's this much better risk measure there. People said, yeah, of course, we've now seen this risk measure, we worked it out on our data, on our portfolios, but it doesn't really make a difference. We are perhaps talking about a couple of percent points in capital. If you think these numbers are then mapped to capital, like some of the rules we saw before. And of course, alpha going to 1 is relevant, because we talk about 99.5, 99.9%. But of course, this is a whole assumption. If indeed, and I've seen that quite a lot, if indeed in risk committees, in the banking world, insurance world, your underlying models implicitly, hopefully explicitly assume multivariate normality or close to that, of course, then I've got this normal distribution. And then I don't expect to see these big differences. This was the story in the late 90s. Then came the crisis and people then suddenly said, well, there seems to be a difference. And for instance, now we know if we have a t distribution, and again, this was on the blackboard, I think now I've got also page 40, then we saw that limit alpha going up to 1, expected shortfall alpha x divided by value at risk alpha x, we had this result, namely this was nu over nu minus 1. Of course, nu has to be larger than 1, otherwise we don't have the mean here. And as we said before, taken nu equals 3, we get a 50% increase in capital. If this is mapped to capital, of course, there's a bit more than just mapping that number to capital. But then we have a 50% increase. That's a huge difference. And I still remember sitting in a, I think it was in New York, in a presentation where we just showed these rather trivial probabilistic results. And people's reactions, chief risk officers from big banks in the US saying, well, this was an extreme eye-opener to them. By now we know, of course, that definitely under stress conditions, a T model is much closer to market conditions. And T3, T4 is absolutely standard model by now. So I just want to show you that the way I see aspects of this course, or certain aspects of this course, is giving you sufficient mathematical tools perhaps to help you discussing these issues a bit broader with people that are perhaps not research mathematicians. So this is result 1 and story 1. Result 2, now I'm getting a bit closer to some of the things I'm going to tell you. Result 2, we know already in general, we know that value at risk is not sub-additive. We have the 3 examples. Perhaps I should make sure that this thing stays alive here. We have the standard examples, very skew, typical credit, very heavy-tailed, catastrophic risk, independent if the alpha is small. So we have, and special dependence. And nobody is going to say to me, well, these things don't happen in practice. Some of these things do happen in practice. So the sub-additivity, the non-sub-additivity of VAR is a major issue. Again, this we made very clear, especially I come back to our work, but also the work of my colleague Freddy Delbaum. We said from day 1, 94, 95, when VAR was born, this is an issue. Why did people not listen? Well, there are many reasons for that. But again, let's do a little exercise. Of course, we know that expected shortfall is sub-additive, right? That we know. Well, let's now do an exercise. Let's now again look at the market situation. Now I have to look at 2 random variables. And suppose the 2 random variables are now bivariate normal. So they're bivariate normal with some mean and some covariance matrix. Well, this fact, but of course, the bivariate normality is a key issue. From this it follows that the sum is normal. I write especially a 1 there because it's one-dimensional normal. I just want to stress it. And remember, going from this left to right, that the sum is normal, I really meet bivariate normality, which is a much stronger concept because I even give you the copula now, the Gaussian copula and the standard on the Gaussian margins. So this is normal. The means just add up. And the variance, we know how to calculate the variance of a sum, is sigma 1 square plus sigma 2 square plus 2 times rho sigma 1 sigma 2. In this case, we just write it down, the variance. Okay. Now let's check the value at risk of the sum. Okay, well, the value at risk of the sum, in the normal case, as I said very explicitly, this is like Black-Scholes. I can give you an explicit formula where the volatility enters. And this is now because the value at risk of the normal random variable, we know, is the mean plus the sigma, the volatility. Here it is, the square root. So the square root of this thing here times the inverse of the quantile. And of course, I now take alpha greater than 0.5. You'll see in a minute why. Of course, alpha will be close to 1, so that's not an issue. And now I use a result, namely the correlation coefficient. We all know that's less than or equal to 1. That's Cauchy-Schwarz. I mentioned Cauchy-Schwarz because it's a norm inequality. And now I'm gradually moving into the next part. This is less than 1, always. Hence, this is bounded by mu1 plus mu2 plus, and now I said if I put 1 here, I just have sigma 1 plus sigma 2 square and the square root. So this is sigma 1 plus sigma 2. Let's again say this is Cauchy-Schwarz times phi inverse of alpha. And there's a less than or equal to 1. Aha, but what is this? This is the mu1 plus sigma 1 phi inverse. That's the value at risk alpha x1 plus mu2 sigma 2 phi inverse plus value at risk x2. And of course, but this is positive, then this is a positive number. And again, now I come back to the story. Why did people say to us when we discussed these issues, yes, but, and believe me, I've seen some of these calculations bank internally. Yeah, but if we do it, we add up these numbers in whatever, they turn out to be subadditive. We have this subadditivity rule, and the subadditivity rule was built into the risk reports. Because that's the subadditivity rule. If you typically place, if you have a global market risk limit, let's say value at risk at some level, it's broken down to the different desks. The subadditivity was built in. And then they started calculating it, and they said, well, it turns out to be roughly like that. Yeah, why is it like that? Now you know. Because somewhere in the systems, in the market, this multivariate Gaussianity played a role, not just Gaussianity. So these, I think, are aspects, at least that I found always rather interesting to observe in practice. And these are the stories which I find personally very important behind the course. That's at least my strong view in this particular field. So we developed this area not just for the beauty of mathematics, but also because it really helped us in shaping discussing with practice. And I still remember being on the board of a company, and I was there I was the head of the risk committee of a bank, that one of the people in the executive board came to me and said, well, this value at risk is interesting, but I add it up, I take one here, I take another one there, I add them up, is that an upper bound? That was a very good question. So that person, he has a physics background. He understood that, but not beyond what the meanings was. So sorry, I wanted to take this out because I think I find these historical stories important because these discussions still go on in practice, believe me.